right, welcome everyone to this session on machine intelligence for open worlds. I'm delighted that all of you are here, and I'll try to be as engaging as possible, but I'll also be throwing out a lot of questions to you. So I do hope that you'll engage and provide your thoughts, because this is an area of research that has only recently emerged in the last 3 to 4 years in the way that I'm going to be presenting it. So I'm really looking forward to hearing everyone's thoughts here on some of the aspects that I'll be covering. So, okay, let's see if I can move this a little bit to the side perhaps, or actually, let's see. All right. I think that's going to be better. All right. So, yeah, just a little bit about me. So I am faculty at the University of Southern California. I hold joint appointments at the Information Sciences Institute, which is kind of a soft money institute in the Viterbi School of Engineering. So we do a lot of research in cybersecurity, AI. AI has become very big, obviously, in the last 25 years. Originally, it was cybersecurity that was the main focus in ISI. We just celebrated our 50th anniversary, so it's an exciting year for us. And I'm also faculty in industrial and systems engineering. So very delighted to be here. I've never been to the AGI conference before, but this is, I think, the perfect year to start attending. All right, so actually, I'm really glad that we started the way we did, because as you will see, it is very related to exactly the problem that I'm going to cover. And unlike us, that we are able to adjust and figure out a way to make things work. But with AI, what I'm going to argue is it wouldn't have been able to actually figure out a way to sort of manage novelty, what we call novelty, something that goes wrong or unexpected, not perfectly smooth, right? However you want to describe that. So let's do an exercise. Let me start with this. I wasn't originally planning to start with this. I was just going to, dive into the material, but I just to do an icebreaker kind of thing. How many of you over here play poker? I'm just curious. Don't be shy. Okay, you do. Anyone else? All right, great. I mean, Sweden is really known for some very good poker players. So, oops, sorry. Okay, I don't want to mess with that now that it's working. Sorry. All right. Okay, so let's go into the first question, and then if you're a chess player, we will also go into that. But let me ask you this question. So you sit down at a game of what looks like Texas No Limit Hold'em, but you quickly learn that this is a special variant where, and in fact, there is such a variant. It's called Crown Hold'em. It's got slightly different rules than Texas No Limit Hold'em, but one of the key differences is that the deck only consists of 9, 10, jacks, queen, kings, aces. Everything else is the same. So you have the straight and two pair and all of that. The different hands that you draw in poker have the same order, same betting structure. You get dealt two hands. There's the flop and the fourth street, fifth street. So how do you change your strategy? What would you do differently? Or what is something that is going through your mind as you're encountering this variant? Could you elaborate? Okay. So that is correct. I mean, yes, the expectation would change. It would go to 0, for example, right? For a pair of twos or a straight that is like, 5, 6, 7, 8, 9, of course, is not possible. But what about your playing strategy? Is there something that you change in the way that you play the game? So you're right, in a way. But what about you? How would you change it? Yes, very good. So much closer. So when you play this game, what you start realizing is that in the normal poker, if you get like a two pair or even a three of a kind, so three of a kind is like three aces, three twos, and so on. It's actually a pretty strong hand, right? So typically when we say when you flop a set, right? So imagine you get dealt like two kings and then a king comes up on the flop. That's a really strong hand. And you want to actually try to maximize your winnings on that hand, by betting smart and so on. But it turns out that a three of a kind is actually a really weak hand. It's something really weak in this kind of game. Even a straight, it turns out, is sort of like a pair. You know how we would think of a pair in a normal Texas Hold'em. Even a straight is actually on the weaker side. Like you could lose with a straight very often in Crown Hold'em. So what you're really trying to go for is something more like a full house, which in a normal game of poker, right? So if you don't play poker, just follow with me. In a normal game of poker, full house is, I won't say near impossible because you do, come up with it every once in a while, but very rare, like very, very rare. Um, in this one, right, a full house is kind of what you're gunning for. So it's kind of like, let's say that you trained an AI and the AI is like, full house, or straight, right? I'm three of a kind, I'm going to win, right? I should bet big and so on. You go bust very quickly in this. So this is, one thought experiment for chess players. I'm going to sort of take a more philosophical turn here, and I'll tell you where the philosophy is coming in. But let's say, hopefully everyone has some idea of chess, right? Unlike poker, even if you don't feel like you play at the grandmaster level, let's say, every time a piece gets taken out, right? So I could take out your piece, you could take out mine, it doesn't matter. An extra row or column gets randomly added to the board. So this is a kind of Hydra chess. There are different variants of Hydra chess where basically the board expands in complexity, when you are in fact trying to simplify it in some way, right, by taking out pieces. So this one is actually fairly simple because you just get more room, right? There's more space that gets added. So would you be willing to bet money that you could at least reach a draw at stalemate against a grandmaster? And we're assuming that you're not a grandmaster, but you have played and you can play a decent game, let's say at the club level, right? Um, I mean, think about that for a moment. If you get a draw or a stalemate, it resolves in your favor, by the way. So it's not a tie. The grandmaster tells you, okay, play against me. If you can at least reach a stalemate, you get the money. So would you be willing to bet on that? And why not? Yes. Yes. Brian. Yes. No, but you're right. You're right. You're absolutely right. So there is a certain kind of reasoning that we do engage in when we encounter a novel situation, right? And as I will show later, it doesn't have to be optimal. Sometimes the answer is not right, but I think what I'm trying to really show here is that we don't come up a blank and say, oh, I was not trained on this, and so I'm going to just not give you an answer, right? seemed like we would be able to do something, which is, and we wouldn't just stop and say, oh, I haven't been trained on this, I haven't learned this, so I'm not going to give you an answer. So that's the key point that I hope you'll keep in mind, as we sort of go into where AI can go wrong over here. So, with that, let me get started by just giving some context here. So typically my projects are in applied AI. This project is a little bit different, as in it's sort of more what we call, fundamental AI. And, lucky for us, there have been like 2 or 3 good projects, really coming out of some of the funding agencies in the last 4 years, I would say. And 2 of the ones that are most relevant to the tutorial today really are common sense reasoning. So that's one of them. It's more tangential to what we're covering today, but it does play an important role. Um, and the one that is really central, that sort of inspired me to propose this, and for reasons I will sort of get into in a moment, is the GNOME project, which is generating novelties in open world multi-agent environments. So that's kind of the name of the funded effort, that we kind of did for like 3 or 4 years. It just recently concluded, actually. And so that was one of the reasons that we wanted to, try and promote the work that we've done collectively as a community, to sort of show you, what happened, where do we stand now, and, where do we go from here. So what is an open world, right? So this is a little bit of an ambiguous term. Sometimes in the literature, you'll see other definitions. But in the way that we see an open world, and again, it's best to start with an example, right? Just to make it clear. So if we start with a bounded example, and I say bounded in quotes because this is something that is completely specified in a way, right? We know all the rules, we know the board, we know the, sort of what's allowed, what's not allowed. And so this is kind of maybe as closed a world as is possible, right? And that's what makes games sort of fun and fair, at the same time. But, just if I introduce a novelty, right? So this is a simpler novelty than the one I showed in the thought experiment. So we kind of just say that, okay, let's add a few more columns here. Let's add another pawn. Not everything is shown here. I might tell you, for example, that you can't, that the board is still, it's non-circular. So you can't go from, in some boards, you can actually like slide to the left and come back on the right, right? Like in a video game. Let's say here I tell this is just an expanded chessboard, but there is a lot more open room. And, how would you, like, let's say you have some understanding of chess, how could you exploit this, let's say, right? And, some might say, well, the best, or what's the piece, right, that will be most affected, perhaps, right, by this. And it turns out it's the rook, right? You don't really need to sort of know too much mathematically to see why, but the reason, of course, is that your rook has more room to come out. It can engage a lot faster. In the board, you don't need to move pawns around before your rook can start engaging, right? So actually, it turns out that the rook suddenly becomes more powerful in a board like this. But how exactly to exploit the rook, relatively speaking, and the best way to do it is something that you have to kind of, think about and play a few games maybe, and see whether your opponent is also thinking about it a certain way. However, the key point I do want to make again is that you don't have to go and relearn this game, right? You might argue this is a new game, that even though it's chess, that there's new positions, and technically speaking, it's different from the regular chess because it's not identical. But we can still sort of see that we don't need to go and retrain, a million times. We don't need to change something very significant. In just 1 or 2 games, maybe even 0 games, we can sort of use our fundamental understanding of chess to reason about how we might change our gameplay, how we might exploit this, right? And that's the ability that we really want to capture in AI. Now, the question is it captured in some of the recent paradigms, right, that we've seen in the community coming out, in recent years, and to what extent, and what else is left to be done? Hopefully, I don't have to convince you that we're still a little bit far from achieving a sort of general novelty adaptation. In some situations, the AI can adapt, but in general situations of where structural novelties are introduced of this kind that requires a shift in strategic reasoning, certainly in one game, right, just drawing on fundamental principles and changing strategy in just 1 or 2 games continues to be something that we are still aspiring towards. So Another example, and one that I was intimately connected with and very interested in, was the game of Monopoly. Now, one reason why I was interested in this is, just like poker, right? There's a very strong element of chance in Monopoly. Um, and there are several, you also negotiate with the other players. There's a social element, although that does not show up in the computational variant. But you do have to trade properties, and in a powerful representation of the game, you can sort of form contracts and things like that, right? Now, in the regular game of Monopoly, again, if you kind of have gone through a Monopoly tournament or read up on Monopoly, it turns out, some winning strategies are if you buy the railroads, because the more railroads you have, the more the rent multiplies. So if you have like one railroad, you get X. If you have two railroads, you actually get, I think, double the normal rent if you land on a railroad, and so on. So, one way to win is, buy all the railroads or as many railroads as possible. Another one is buy Boardwalk and Park Place, right? Those are the two expensive blue properties right at the end. So basically, as you go around, the properties become more expensive. The rents also climb up, everything climbs up. So if you buy Boardwalk and Park Place, then build houses and hotels on that. And if I land on your property even once after you improved it, I'm basically going to go bankrupt. It will only take me like just once I have to get unlucky and land on Boardwalk and Park Place that is improved and I go bankrupt. But what if I told you that the red properties are rent protected, right? So suppose you're not allowed to build houses and hotels on the red properties. Well, to you, it would seem really almost trivial, right? You might think, well, I just wouldn't buy red properties. Why would I do that? I have no chance of winning the game. I'm spending the money. I'm not going to get a return. And you can kind of reason very clearly to me why you would not do that. Um, and it turns out that we have actually evaluated reinforcement learning and some other pretty state-of-the-art algorithms, and they can't figure it out. Somehow they have internally modeled that red is a very good property. It's in the middle zone. It's not too expensive. It's not too cheap. It actually gives you really good value for money. But the moment it becomes rent protected, somehow the brittleness really comes out in these algorithms. They're unable to adapt quickly enough. They need to see many, many games before they can come up with a solution. Now, needless to say, right, the real world is an open world. So the term I like to use for the kinds of novelties that we are interested in are black swan novelties. So who's heard of this phrase, the black swan? Great. And can you tell us where you heard it? Or yes, and what's why did he use that phrase? Yes, exactly. So it actually does exist. And it also happened with flamingos. My nephew, he was arguing with my mom because she was like, I saw a red flamingo in the Los Angeles Zoo. And we were like, no, there are no red flamingos, there are only white flamingos. So, so I'm like, okay, the children are especially sensitive, it turns out, to black swan events, black swans generally, and animals that violate expectation. But yeah, black swan events can and do happen with non-trivial frequency. And there's been a lot of study on why this is. Basically, what has happened is that there's now a very clear understanding that we used to assume, normality for, just like with heights and weights and so on, which do tend to follow a normal distribution. We sort of thought that, world affairs, if you will, also follow a normal distribution. The normal distribution dominated discourse. Then it turned out, right, with the growth of the web and availability of a lot of data and so on, that actually it's more like a Pareto distribution, right? So, the fat tail, the long tail is actually not it doesn't go down quadratically. It's more scale free. So the way you can think about it is that financial crash is actually a very good way to think about it. So stock prices, right? If they were distributed normally, by and large, if you think about it, right, the probability is proportional to e to the minus x squared, like, right? So the log probability is proportional to minus x squared. So it goes down very quickly in that space. But it turns out it's actually more, when you look at some of these events and event types, it's sort of more like the probability is the probability is proportional to um uh sort of x to the minus gamma, something like that. It's where, so it's a power law distribution. So if you take the log on both sides, you get a linear, it's like a linear slope. So the unexpected events do go down, they become less probable, but they become less probable linearly, not quadratically, which means that these events are more likely than we think they are, right? And they will occur, with some non-trivial frequency. So this is the long tail phenomenon. And, the pandemic and financial crashes, 9/11, unexpected wars, right? Obviously, there's one very close to here. UFOs, meteor crashes, etc. Right? We keep hearing that there's just, I think this week there was news that a meteor or asteroid, I don't know, size of the Empire State Building is just passing very close by. In California, we had droughts for so many years. This year, we had 12 atmospheric rivers. It was rain after rain after rain, right? No one expected it. We're out of drought now, but we might be entering drought again, right? So it's just, there are lots of novelties in the real world, and there are lots of violations of expectation, and a lot of surprises, whatever word you want to use. So of course we want, we haven't dropped dead, hopefully we are still adapting, and we are still, resilient, reasonably resilient. So we also need AI systems to be like that. So agenda for today, right? The rest of the agenda for today is that I want to more formally introduce some of the work that we've seen in the last several years, which also builds on a lot of other work that's been happening over the decades, to open worlds and novelty. And so I really want you to think about novelty. One of my goals in this session is to sort of unravel the black box of novelty, so that you can, when you see a novelty, you can actually put it in a framework. And this is not, a framework set in stone. It's gone through several iterations, but you'll see sort of what is so interesting about that, this question of what is novelty, and how do we, even practically speaking, even if we discount the philosophical aspect of it and go into the practical aspects of novelty, what are the different types of novelty? How do we deal with different types of novelty within an AI framework? And then the second section, where I really hope that we can sort of have a discussion, is how do we evaluate open world learning? And I'll just give you a primer on why this is a challenging problem. So let's say that I am building a system that is supposed to react to novelty, that's supposed to adapt to novelty. Well, the issue becomes that if I'm building the system, I can't be the one designing the novelties. If you think about it, right? And I can't even look at the novelties. If I'm so much as aware of the novelties, let's say it's in some test set, training set, it doesn't matter. Even awareness of the novelty, it turns out, can really bias my model selection. That, I may inadvertently or advertently leak knowledge into the system, tune the system in some way, make it, and so the novelty is not really a novelty. So, but then at the same time, if I'm not told anything about the novelty, how can I build a system? What's even the language for expressing such a system? So there is a bit of an interesting challenge there that I'll sort of tell you how it was addressed within this DARPA program that funded this work. In the second section, I want to switch a little bit to common sense reasoning, because one of our hypotheses is that in fact, if we really want to build a truly robust open world system, we need common sense. Without sort of a big variety of common sense in the system, and common sense knowledge in the system, we cannot really have open world learning. Now, this, it may not be the only thing that is needed, but we sort of believe, right? And I'll sort of try to present why we believe that we do need that common sense reasoning and open world learning kind of go together. Now, after that, I'll go into an example system, but this is not a system for open world learning itself. It's a system for novelty generation, because that was my angle in this project, which is that how do we generate challenging novelties? How do we think about novelties? And we kind of built the test bed and the novelty generation, and then we used the test bed to evaluate systems that were built by other teams. So it's a slightly different angle. I'm not here to sort of, tell you about the techniques for open world learning. How do you do that? I think that I will point you to some pointers on that, but we won't go too deep into some technical approach for open world learning. And then finally, research opportunities and concluding thoughts. So maybe before we go any further, so any questions? Yes. Sorry, similar to? Yes, yes, correct. Well, there is one difference though. So, um, typically what we really mean here when we talk about open world learning, although you're right that you can think of it as and when you design the system, you do have to think of it that way, that not everything is specified and things can change. But I think one key difference is that we want a system that will work very well in the default environment. So the default environment is not partially observed in that sense. It is the normal game of chess. It is not partially observed. We see everything. But then there is a major structural change. So it's almost like you're playing the game, you win the game, but then in the next game, I change it in some way. So it's kind of like, but you want the same system to then be able to detect the novelty, to figure out what's changed, and then to adapt to it. But it should also continue to play the normal game well. So it's kind of like, maybe that's sort of a difference. But you're right that when you're designing the system, you have to think of the world as partially observed, but the default environment is actually fully known. And so the real test is that do you understand the domain well enough? And do you have the fundamental principles locked down well enough in the system that it can then apply those with some general learning to uh, deal with novelty as it may come along? So we haven't addressed that particular problem in this program, because it was thought to be too challenging initially. I mean, some people did try to present the general game playing architecture, but we figured that, and by we I really mean that everyone involved in the effort, and I'll say a little bit more about the effort and how it came about and who, like how people were funded. But basically, the way that it worked was that each team that was generating novelty proposed a single domain. So we proposed monopoly. There were others who proposed computer vision tasks, and there was one team that proposed like a 3D world navigation task, and so on. Um, and then there were a second set of teams that had to build the open world learning agents. And so the way that they were told to approach the problem was that every 6 months they had to work with a new novelty generation team. And they could build a different system, but it had to rely on a fundamental architecture, underlying it. But purely in terms of implementation, it's a very hard problem to be able to deal with several different games at the same time, unless you have a very common language and so on. So no, we didn't quite go into that more ambitious problem. In a way, we focused on one domain at a time. But yeah, the goal was to be general, not to fit to one domain. Yeah. So open worlds, are characterized by novelty. So novelty here, pragmatic definition is that it's a state or situation that violates implicit or explicit assumptions about agents, the environment, and agent-agent and agent-environment interaction. So this is actually a definition that was taken straight out of the sort of the call for proposals, where we tried for this. But I thought it was a pretty good definition. I mean, I tried to come up with another one. I could probably make it even more abstract, but I think this definition that was in the original call for proposals hit the sweet spot in a way between something that is pragmatic, where we can sort of see what might violate assumptions, but is also general enough. It's not too specific, over here. So why is open world learning worthy of study in its own right? And so here I always like to cite Pat Langley's work. So he's been in this community for a long time, and I got to know him closely because he was involved in this program. And so he published this paper, I believe it was in 2020 in AAAI, sort of a thought paper. He's since updated it a little bit, but the original paper was still, I think, the sort of the clearest way that that I could find to think about this. So he says, I pose a new research challenge to develop intelligent agents that exhibit what he calls radical autonomy by responding to sudden long-term changes in their environments. I illustrate this idea with examples, identify abilities that support it, and argue that although each ability has been studied in isolation, they have not been combined into integrated systems. And then he goes on to say that he's proposing a framework for characterizing environments, specifying the ways in which environments can change over time. So this is a novelty question, but he doesn't develop novelty as fully in this paper. And in subsequent work, we end up developing it a lot more. And in closing, you outline some approaches to empirical study, but again, he doesn't go into evaluation. And this is also something that was developed a lot over the course of the program. So here's what I want to do at this point. So I will go a little bit into his framework, but then I want to show you the actual call for proposals to sort of show you what the challenge problem was, in response to which we wrote these proposals and ultimately formed a community and sort of started working together on this problem. So, Langley defines the task of open world learning as, given, right, an agent architecture that uses expertise to operate in a class of environmental situations, expertise that supports acceptable agent performance in this class of environments, limited experience with an environment in which sudden unannounced changes degrade performance, find, right? So the open world learning problem is to find, given all these things, when environmental changes occurred and what revised expertise will support acceptable performance. So this is taken verbatim in a way from his paper. It's a little abstract, but very useful to kind of think about the problem itself, right? So when he says when environmental changes occurred, what he's really saying is that even detecting novelty can be a challenging problem. In fact, when you think about something like concept drift that some of you might have heard about from many decades ago, or anomaly detection, right, fraud detection, and so on. These are sort of, if you think about this in a very general way, this is detecting when an environmental change that is important to you and your task has occurred, right? So if it's fraud detection, then you're clearly interested in, whether some transaction is a fraudulent transaction. It's going to cost you money, obviously, if you don't detect it and put a stop to it. And so there's the novelty detection challenge, right? So that is one, but even more broadly, it's not enough to actually detect the novelty. You also want to characterize the novelty. This is a very interesting problem in a way. And what revised expertise will support acceptable performance. So this is a novelty reaction / adaptation / learning, right? And so this one is more like, incremental learning, or some kind of revision to your knowledge base. A whole body of techniques have been proposed over the years. But, how will you basically get acceptable performance? The one thing that he does not say here that I think makes this a little bit more incomplete than I would have liked, and I think he since perhaps revised the definition, is what do we mean by acceptable over here, right? And you could sort of theoretically claim that once I have detected the change in the environment, then let me go ahead and retrain the reinforcement learning, just to take an example, a million more times on the revised environment, and again I'm in the same sort of paradigm, right? I mean, we know it will work very well for many problems of that nature, right? Where you get the reward from the environment. There's a deep net to, give you robust nonlinear strategies. But what he really means by acceptable over here is that you only get limited number of tries, before you can adapt. So the example he uses is an autonomous vehicle that is operating underwater, because he was kind of writing for DARPA in a way, and he wanted to bring up, military technology and examples, right? So imagine you have an autonomous underwater vehicle. It's roaming underwater. It's been trained to do that. It's doing okay, but now it's in the ocean. And no matter what you do, the ocean is an open world. I mean, they're saying that we still don't know enough about it. We know more about space and about Mars than we know about the ocean. Like literally, I think I heard someone say that we know more about Mars than we do about the ocean on planet Earth, right? So you encounter a volcanic, bend, right? Or which is, and there are volcanoes on the underwater floor, or, some big creature, that is knock you off course. And maybe one of your sensors fails, or you get into a current, right? Or those kind of things. You can't anticipate everything. Autonomous cars are actually learning this firsthand, that despite a lot of experience and training data and so on, there's still a lot of things that they simply don't anticipate. Whether adversarial or just plain natural, that occur in a natural environment. So it's not, it's what abilities are really needed here, right? So here again, he's a little bit formal, but I won't stop too long over here. But the key, it's usually what you would expect, right? So there's a performance element. This uses known expertise. Um, there's a monitoring element that compares observations with expectations, right? This will prove to be important. Others will expand more on this. There's a diagnostic element. This is kind of what we call a regret measure, where um, you're trying to, so in the poker example, right? Let's say that you haven't thought it through perhaps, and you get the three of a kind, but then you find you lose, right? Someone else gets a straight, then you again get a three of a kind and you again lose, or maybe you get a straight and you lose to a flush or full house, and it's occurring more often than you would expect in a normal game of poker. So now you can try to diagnose, right? You're monitoring your performance. You're using known expertise. The known expertise is three of a kind is good, straight is good, I should be winning. I'm monitoring, but then suddenly I stop winning. So then I try to diagnose, right? Like what's going on? And maybe now I realize that, oh, the probabilities have changed dramatically. The three of a kind and straight are now much more probable. So I should not rely on winning or betting big with those, right? And so, and so you have to generate hypotheses about the cause, you evaluate alternative candidates and you select among them. And then there's a repair element, right? So this is where you do the learning and you try to figure out, what you can do to actually start performing well again, right? And again, the hope is that all of this is at a very fundamental level, that you can't really rely on gradual statistical kind of changes or learning. And that's a very important aspect of this problem, that the statistical underpinning of much of the learning that we see today is gradual, if you think about it, right? So you do the SGD, for example, or you do some kind of optimization, and it's supposed to be like a very gradual search in the space, and you need a lot of data for that reason, right? To actually find that local minima that you hope is going to be as good as a global minima. But it is gradual. It's not very sudden. You can change the learning rate and do other things, but it turns out that if you do those things, you risk making the algorithm unstable. It's not meant to be done in that way, right? The goal is you do move slowly in the space and eventually converge on a very good solution. This one is very sudden. It needs to happen much more quickly. And so the view is that statistics matter, but you can't rely on statistical learning alone over here. Something more is needed, whether it's some kind of symbolic learning or whatever it might be, but something more is needed over here for this. So the real question is, what is that something? So on that note, what paradigms are relevant, right? And here, you're going to see some things that some of you might be very familiar with, somewhat familiar with, etc. But here are some things that he proposes in his paper, where he's like, well, model-based diagnosis and repair could be one option, but it turns out that in these kinds of models, the model has to be very well specified. And it focuses on very specific cases for that reason. Plans, right, is another one. Metacognition, which is becoming, again, very big and definitely has a close connection to open world learning. Problem reformulation, right? Change detection, theory revision, scientific discovery, which finds laws and models to describe or explain observations. So this would be more like, computational scientific discovery and reformulation. And then transfer learning, some kind of transfer learning on overdrive. So that, because if you think about it, when you go from the old version of chess, the default version, to the Hydra version, it's a little bit like transfer learning, right? We're not going and learning a new game. So we are transferring some knowledge, but there's other knowledge that we don't want to transfer, right? So that's kind of a framework for thinking about this, at least, right? That, okay, there's a lot of knowledge I do want to transfer. There's other knowledge that perhaps I don't want to transfer and that I want to relearn or I want to advance in some way. So, his theory here is that some combination of these techniques is really required, especially if we want something more like an AGI open world learner. And, probably all of these or some of these would together hold promise for an integrated solution, and more researchers should pursue this objective rather than, place their bets on any one of these, basically. So open world learning requires an integrative approach to adapting to novelty. But on that note, what is novel, right? So again, rather than give you my thoughts per se, I've tried to choose thoughts from others that I think are illuminating. So here, right, these are two quotes from this paper that was again published in Triple AI, the senior track. And again, all of these people who are in this paper were all involved in this DARPA program, that under which we were involved as well. So while significant research has been undertaken in these areas, a noticeable gap exists in the lack of a formalized definition of novelty that transcends problem domain. So in this paper, they kind of point to the fact that novelty is something that you see it and you believe it's novel. You have an instinctive view of what might be novel or not novel, but a formalized definition of novelty has actually been really hard to come by. And with decades of work and thousands of papers covering novelty detection and related research, then anomaly detection, out of distribution detection, open set recognition, and open world recognition, one would think that a consistent unified definition of novelty would have been developed. Unfortunately, that is not the case. So, one of the questions we have to ask really, right, is novelty the same as surprise? And is also the same as violation of expectation. So these are two words that you will also see a lot in the literature, especially in the cognitive science. But so is it the same now? We had some very heated debates, in the program about this. Is it the same as surprise? I mean, I'm curious what the audience thinks. Is yes. Oh no, that's fine. We want to hear diversity of opinion on this. But who else? Yes. But would you say that in either case you were also surprised? Okay. Um, okay, so I think yeah, this is important, but no, that's valuable. Who else? All right. So for practical purposes, yes, in a way. I mean, of course, we're not saying they're identical, by the way, right? So there are these differences, that some could be pleasant, unpleasant, etc. Philosophers do disagree. In fact, there were, a couple of people who had some background in philosophy, and they would vehemently disagree with a lot of other things that were said. Computer scientists were actually very easygoing. What I learned, in this program was that computer scientists are actually very, very easygoing when it comes to such questions. Like, let's just get something practical, and do something practical. I mean, we're not going to be able to resolve this question. So, um, so there are interesting counter examples, especially when we consider human cognition. So some people say, well, and the philosophers made this argument, but I can't really speak for them here, that it's not the same as surprise, not the same as VOE. But there were some interesting counter examples, but they were very philosophical and involved. But here's the problem, right? So if we say no, the alternative might be, and so this is again coming from the philosophers, the alternative might be ontological predestination. So something is novel if I say it is novel, right? So I might say that the fact that this room is round, right, is novel. and and that rooms should not be round, rooms should be square, rooms should be rectangular. But then that seems to be arbitrary, right? Like why it doesn't seem like that should be that surprising. Um, so ultimately, because surprise and VOE seem to have established meanings in psychology, and this is the main point I wanted to make, because you might wonder why the word novelty. And so one of the reasons why this word became used a lot in this specific context is because we wanted to avoid the kind of psychological connotations of surprise, which does tend to be associated with sort of negative emotions. Although the dictionary definition would not suggest that, but in practice, we do see that. And VOE, it turns out, also has some like kind of maybe through norms, because the papers that were published, it's associated with certain things that are studied in psychology. So let me show you an example. So speaking of humans, are we open world learners? Well, hopefully I don't have to convince you that we are. We may not always get it right? But coming back to the thought experiment we did at the beginning, we are able to satisfy in most situations. This is a really important word. I love this word. I came across it in sort of a more psychology setting. But, we are able to satisfy. We're able to come up with solutions that are good enough, right? So whenever you hear someone say, well, close enough, good enough, right? I'm not looking to be perfect. That's when what they're saying is it's okay to satisfy. You don't have to be optimal. You don't need to get it right to like 10 significant digits. So VOE and responding to VOE is kind of wired into us actually, and we can see it in infants. Now, you may not be able to make out all the text here, but this is actually from another call for proposals, this one from Machine Common Sense. It's kind of worthwhile looking at this. This was a very impressive chart, that was based on a lot of research that this program manager had compiled and cited and compiled this chart based on almost like a survey. And it turns out that when you look at something like, unseen objects can cause visible outcomes. Like you actually see the violation of expectation occur very early on in infants. Like, and you might wonder, how do we know this? Because we can't talk to infants, right? But a lot of the things that you see here are, they're not really abstract. So when we talk about objects and outcomes and so on, you can actually do the experiment. And so I believe that a lot of these, ultimately the way that they know that there was a VOE is because there's like some kind of camera or something that they put in that they install somewhere, and then through facial recognition, because when the infant goes through a VOE, they're not trying to hide their emotions. So you can actually make out immediately when the infant has a VOE. And so they've done this massive home study where I believe it was done out of MIT, where participants would come in, like, moms and kids, their little infants, and there would be some kind of camera setup or something like that where where they would record the infant's face over a relatively long period of time, and they would do controlled experiments and kind of see whether the VOE registered on the infant's face when they did the experiment. And it turns out very consistently. I mean, there is some margin, but overall the results are very consistent for some phenomena. And you can sort of see here that the sort of core objects domain. So the fact that objects have depth greater than 2D and move in 3D space, objects move separately from one another except on contact, these kinds of things, very physical reasoning, tend to occur very early on. And if you do something that is very unexpected, and they can manipulate that in the experiment. So I'll give you an example. Let's say there's a bed over here, okay, and you roll the ball under the bed, and the ball is rolling fast. So you kind of expect it goes under the bed. So now it's hidden, right? Now you might think this is obvious, but the object has gone out of sight. So if you don't know any better, it could be that the object has disappeared off the face of the earth, right? And in fact, for a very short period of time, the infants are willing to believe that, it turns out. But there's another period of time where if the object does not come back out the other end, if the ball does not roll out the other end of the bed, then you will see the surprise on the infant's face. And this is a very consistent and sort of and it occurs within that age group, certain age group, for most normal infants. So and then theory of mind, right, is sort of well known to occur by like 5-7 years old. I forget the exact age, but I believe it the famous doll experiment, that some of you might have heard about for theory of mind. Who knows? Does everyone know what theory of mind is, or should I explain it perhaps a little bit? So yeah, so theory of mind is that I have a mental model basically of what you believe. So the experiment that was done was that there were these two, let's say you have two humans. Okay, so maybe let me think about it this way. So suppose I have two boxes, and there's a doll in one of the boxes. Okay, and there's another person sitting here. Um, and then there's a third person, let's say, and then, or let's say there's a person, and then the person goes out of the room. So the person knows that the doll is in the first box. So they've seen me put the doll in the first box, but then they go out of the room. And while they're out of the room, um, I take the doll and I put it in the second box. Okay. So they don't know that I put it in the second box. Now let's say they come back into the room and they have no reason to believe that I've done anything, that I've changed anything. Now, if a third person were to ask me, I was in the room, were to ask me that let's say I'm Mary and the other person is Sue, who went out of the room. So if I am asked that if Sue is asked to pick out the doll, which box would she go to? Right? I would say that she would go to the first box because she went out of the room. That's when I switched to dolls. She has no reason to believe otherwise. So when she comes back and she would go for the first box, even though I know that the doll is in the second box, right? So in other words, think about what I'm doing. I actually have a certain model of what Sue believes, right? Now, Sue may not do that. Sue may be suspicious and Sue might go for the second box. So the question here is not what is right or wrong. The question is that do you have a reasonable belief of what Sue is thinking, of what Sue's knowledge base is? So this is what we call theory of mind in psychology, to explain it simply. And they've done experiments on this, in fact, a variant of this exact experiment, and it's done with dolls, and there are two girls, and I believe they are 7 years old or 5 years old. I forget the age, but that's the age where the theory of mind is found to occur. If you do it before then I don't believe it occurs. And by 5, 6, 7, around that time, the theory of mind occurs. You can sort of see it empirically, that the girl answers the question correctly and is able to ascribe where the other girl would look for the doll. To us, this seems obvious, right? But what I'm trying to say is that even these abilities that you take for granted, there have been lots of studies, and this is, I think, a very great thing about the modern psychology and cognitive science that has happened in the last 20, 30 years, maybe earlier. Kind of started with the infamous conditioning experiments, the Stanford prison experiment. And so those were infamous. But since then, right, there have been many, many good experiments where we now have a somewhat detailed understanding of when some of these very basic abilities arise in humans. By the way, theory of mind is still controversial, even in the large language models. There were 2 or 3 papers recently where one paper said that the large language model ChatGPT, GPT-4 has theory of mind. The other paper says no, it turns out it's like an artifact. It doesn't actually have theory of mind. So we still don't know whether even large language model has theory of mind. But those are the kinds of abilities probably that we need, right? To, especially in agent interactions, one might argue, to have open world learning. So one of the challenges of open world learning, and this is kind of paradoxical, but not quite, seems to be that machines have a better shot at approaching optimality or near optimality in closed worlds than being remotely closed to satisficing in open worlds. So it's almost like extremes, right? And this, of course, you might have seen in other guises, machines can be brittle, right? So we know they can be brittle in many different ways, but this is a different kind of brittleness that I want to point you towards. It is brittleness. It's a lack of robustness, but a different way to think about brittleness. So what we're saying here is that if I give you chess, right, what we've seen is chess, Go, etc., with the right technique and the right computational power, and not to discount the advance, right, itself and the scientific merit of the work. But the truth is that what we have consistently seen is that once we are given the problem, we're able to get, really optimal at it. But then when it comes to something like, where you change the world in some way or you try to make it generalized, it doesn't even satisfy, it tends to break. So it's almost like you get all or nothing. You get like superhuman performance or it breaks. right? You can't get satisficing in the second world, at least, as far as we can tell consistently. So, here's the Bolt paper, right? The one that was in AAAI. They do present a very abstract framework. I won't go into all the details, but I did want to sort of show you that there is, a more mathematical sort of way to think about this, especially in the computer vision world. So a lot of these researchers who wrote this paper came from the computer vision world, and um, what they sort of say. So without going into the boxes, hopefully kind of look clear. So the dotted boxes, you don't observe. So the agent can only access world information indirectly through a perceptual operator. So there's a world, there's an observed space, there's an agent, right? And the agent accesses the world space. Again, these are abstract notions, but the terminology hopefully is not too unclear. So the agent can access the world state through a perceptual operator. So I see what is happening right now, right? And so there is a world state, but I'm accessing it through my visual, my perception in a way, right? Um, and it can then update its internal state and act on the world state. Items with dashed outlines, so those are the three things you see below, are outside of the task or agent, but are critical to defining novelty. In the framework, a theory of novelty is obtained by specifying the world dimensionality, observation space, accessible to the agent. I mean, there's a lot of terminology. I mean, that's one of the disadvantages, by the way, of this, which is that it's too abstract. It's too terminological, but it does contain some of the core elements that one would argue is needed for a good theory of novelty. And two things that I want to draw attention to, again, won't, sort of stop here and with this, framework too much. You can sort of read the paper if you're interested. But I do want to point to two things, one of which is this dissimilarity operator, and also this thing called the regret function, right? So the dissimilarity measures, right, are task dependent and measure dissimilarity between items in the world space and the observation space. So, this is kind of what is telling you that the world has changed, right? If there's a high dissimilarity. And what they're saying, again, they are kind of non-committal. They're saying that this could be an actual distance metric. This could be a statistical measure. This could be information theoretic. And if the world modeling is probabilistic, then it may but need not be based on probabilistic computations. And so one reason why they don't define it as a metric is because human perception is known to be non-metric. Now, one of the advantages of this framework is that it does yield some abstract novelty types. So this is very interesting for problem solving, right? So unanimous novelty is any world novelty W for which the perceptual operator produces an observation space state that is both an observation novelty and an agent novelty. Unanimous novelty is correctly detected by the agent. So they make a distinction between observation novelty and agent novelty. And agent novelty here is something that changes the way that the agent would behave, right? So you might observe the world is different, but it still might not change the way that you behave. So here, right, unanimous novelty is, okay, I see something has changed, I'm going to change my behavior. And so it's a correct detection. There's imperceptible novelty, right? And so the agent cannot directly react to such novelties. There's faux novelty, there's ignored novelty. So they do define these different types of novelty. And I think that is one of the more useful aspects of this framework. But some of the criticisms are that it's too abstract, first of all, right? It's too difficult to instantiate in concrete environments with sufficient specifics. I mean, there are way too many symbols, right? And how do we define all of those for chess, for Monopoly, etc.? Then it turns out even when you work through some of the terminology, it's better suited for perceptual domains and action domains. So why did I want to bring this up? To make the point that, perhaps we need to think simpler, even though it may not cover everything, right? But we might be able to reason more about novelty if we can be simpler. So an alternative approach that we kind of took right from the beginning was to define what we call a novelty hierarchy. Now, the reason why it's a hierarchy is because on the leftmost side, right, and this is just the first version, you sort of see, like bigger subtypes, right, like entities and attributes, interactive and then external. And within each of those, you see different, like more fine-grained types of novelty. So according to this hierarchy, the level 0, right, is basically like normal training, testing, machine learning, right? So if you think about it, the test set is also novel in its own way, right? Because you haven't seen that during training, but it's coming, the understanding is it's IID in most tasks, right? It's coming from the same distribution. It's just that you haven't seen the specific instance, but the distribution is supposed to remain the same, at least theoretically, right? So this is what we call an instance novelty. It's just previously unseen objects or entities. But it's sort of interesting because we can think about this as the base, the simplest kind of novelty that applies to learning. But then we might see unseen classes of objects or entities, change in a feature of an object or entity, such as color, shape, or orientation. So let me give a concrete example. So a class novelty might be in Monopoly, right? Along with house and hotel, you might have a third kind of improvement. So let's say it could be a duplex or a big compound or something like that, right? Where you can improve the property now, not just by building house or hotel, but by also building something else, a third class of entity that didn't exist before, right? The attribute is change in a color. So maybe I make the blue properties green. What would that do to the gameplay? We would now have like 5 green properties rather than 3 green and 2 blue. It would be harder to monopolize, but if you do monopolize it, then the odds of winning go up a lot more, right? If you think about it, if in Monopoly, you have to capture all of the properties of the same color before you can improve, right? Representation, this was very controversial because it was system dependent. And it's exactly what it sounds like. How do you represent the sort of the board or the world and so on? Relations, interactions, capabilities. I will go into, I won't sort of give you an example for each one, but I will show you examples for a more sort of recent version of this hierarchy in just a bit. So the problems with the initial hierarchy is that the categories sound reasonable at first glance, but then run into severe vagueness issues, right? So just looking at this, can sort of anyone see perhaps where the vagueness issue might arise? Like, is there a novelty just looking at this, and you're just looking at this now in a way for the first time, but is there a novelty that you can think of in any domain where it could fall in any one of the, in more than one category, let's say? So it's not clear. Is it a class? Is it attribute? What is it? Yes. Exactly, right? So that could be one. Another one is that if you change like the very last one, right? Like one might argue that if you're changing anything in the levels of the entities and interaction level, then aren't we also changing the environment in some way? Aren't we changing the context in some way? So those are especially underdefined, right? Because one might argue that any change in the previous level could be a change in, could also be a level 7 or a level 9 change, and so on, right? So, but yes, also that, and yeah, so it's kind of, it runs into these vagueness issues, and it turns out in practice, the issue is actually quite severe. It's not just a theoretical issue. A lot of times, there were a lot of disagreements between the teams that were building the learners and the teams that were generating the novelty to, kind of define more clearly what the allowed novelties were in a test situation. So the initial assumption behind the hierarchy was also that novelties further down the hierarchy will prove more difficult than novelties up the hierarchy. But experimentally, this did not really pan out over 3.5 years of experimentation. In fact, what we found was that in many cases, it's the middle novelties, the interactions, relations, capabilities that turned out to be very challenging for agents. The first few categories and the last few categories, were more sort of were more black and white, in the sense that either it succeeded, and if it succeeded, then it succeeded really well, or just broke. It could not figure out. So it was like, either you get like complete failure or you get the success that you would normally expect. But for the middle one, even when it did detect the novelty, it could not quite figure out how to handle changing interactions or changing capabilities of the other agents and so on. So this proved to be difficult. Um, and more generally, right, why this hierarchy? Is it descriptive? What do we want the hierarchy to do ultimately? Are we trying to describe all kinds of novelties in the world, right? Do we want to be descriptive of novelties that we do see in the world? Or do we instead want to be prescriptive, right? That these are novelties we want the system to handle. We don't care about all the novelties in the world. What is our goal behind designing such a hierarchy, and how does it fit into broader frameworks or theories, such as those by Bolt or Langley? So after some iterations, so these were iterations that occurred several times. So after some iterations, we came up with a slightly new hierarchy. This one is more simplified, and so now you have, like, instead of entities and attributes and environment, external and so on, it instead was single entities, multiple entities, and complex phenomena. This is kind of almost an umbrella term, so it was still not completely satisfactory. But the nice thing now is that, first of all, the representation went away. So we wanted to make this independent of the system, right? We want the novelty generation to not be tied to any one system. So we got rid of representation. Instead, we have objects, agents, and actions. So one of the other criticisms of the previous hierarchy was that it wasn't making a distinction between objects that sort of had volition, that could make decisions, that were like other players in the game, even if they were computational, versus kind of more static objects, right? Like houses and properties and chess pieces and so on. So it turns out that, you do want to make a distinction between them because you deal with them in very different ways. One is arguably much more complex than the other. So, the TA2, where you see the TA2, by the way, over here is the team that is building the OWL learner. And the TA1 is the team that is doing the testing, that is building the novelty generation, basically, right? So the two are independent. So, these kind of these are pretty mnemonic, objects, agents, actions, relations, interactions. Then it sort of gets a little bit more vague. So environments, goals, and events. So let's take some concrete examples. Each novelty type can be further distinguished in terms of the novelty being class or attribute. So this is a small detail, but you'll see what I mean. So these are many different domains that were sort of implemented and or tried within the DARPA program. And so I'll pick one that I think everyone will understand, which is chess and autonomous vehicles. So you kind of see those towards the end. So, an example of a new class might be a new neutral player can move. So a third player can move any player's piece every 5 turns. And the new attribute might be that an existing player uses a new opening strategy. So again, this, you might think, well, is this really an object novelty? And so the controversy starts arising sort of immediately. The autonomous vehicle, a new dog is added to the environment. An existing human has a different color clothing. So it's, then here, right? So actions. So an existing opponent can now remove a piece from the board temporarily for one or two turns. The attribute version would be an existing opponent now takes more time for each move. For the autonomous vehicle, an action novelty would be an existing human can now jump when they couldn't before. And an existing human can now run faster and so on. It can be a little difficult to see how these novelties might affect a learner. These were meant for, illustrative purposes. But, you can sort of see that there's something unsatisfactory, in a way still, right, about this hierarchy. I mean, it's not bad. It is trying to capture a different kinds of novelties, but there's still a vagueness problem. And there's still this issue that the examples seem a little bit arbitrary, right? So maybe let me ask, if you had to design a hierarchy, how would you do it? Like, how would you try to categorize all the different novelties out there? Like, if suppose you had to design from scratch and you had to kind of figure out a somewhat general framework, for categorizing the different types of novelty that are interesting in the world. Like, what would be your approach? How would you do it? Or would you think about it in a top-down way from your own experience, or would you do it like what would be your approach? Yes, very good. Yeah, yeah. So I think the program manager had tried to do that. He didn't go far enough on that, but he had tried that approach in a way. The approach that we had recommended, it didn't get implemented, but the one that my team had recommended was that for a lot of games, we do have a lot of variants online. So for the big games, I mean, not just chess and poker, but like World of Warcraft and you name it, right? I don't know, Dungeons and Dragons, etc. Right? You have like many different variants that are popular online, and so we were thinking that we do a case study not by coming up with our own novelties, but by going and looking at all the many variants of these different games, and then trying to see if we could cluster them and try to form the patterns and so on. So we told the program manager that maybe we should try to do that, and so he recommended, well, that basically he told us, you guys should go ahead and do that, but uh, no one is under an obligation really to accept the recommendations, and you're kind of taking a risk. The effort might not go anywhere. So we were like, let's just go with what exists. So there are better ways to spend time, right? But that's the way we would have preferred it as well. So relations, interactions, again, since we're coming up on the break really quickly, I want to make sure I show you something before we break. So one of the more recently, when the program came to an end, we were invited to write a perspective article on this in Nature Machine Intelligence. So this is an article under review right now. And in an under review article, we kind of went through some of these problems and we proposed a simpler hierarchy. Again, so our view was we need to go simpler, not more complex. We felt that the problem that can arise is that we have this instinct, this urge that if something is not quite making sense or it's vague, etc., that make it more complex, make it more abstract. And we resisted that. We were like, no, let's make it even simpler. We might leave out some classes of novelty, but how can we make this as concrete as we really can in another try? And you can sort of see the proposal we made here. So again, we have, instead of single and multiple entities, we've now decided to go for entity-based, relation-based, and environment-based. But in environment, we are now much more specific. So we say that environment-based novelty is one where either you change the rule, right? So a direct change in removal of or addition to the set of rules governing the task environment. So an example from chess would be that in addition to checkmating the king, the winning player must have at least 5 pieces remaining on the board. Otherwise, the game is declared a stalemate. So this is a rule change in a way, right? We're saying that, okay, the rule that determines whether you won the game has changed in some way, right? So now we don't have to decide that, okay, is this a context change? Is this an environment change? It's a goal change, right? Like none of that. It's a rule change. There's been a change in rules. There haven't been new objects added. Um, there's not a new agent or some kind of agent novelty. In the relation-based novelty, we further say that there are two kinds of novelty we're looking at. One is affordance. So the word really comes again from cognitive science and that world where there's a change in your capabilities, basically. So a change in the ability or capacity of an agent to interact with an object. So players can move bishops in the forward direction, but not backward. So affordance doesn't have to be positive. It could be negative. It might restrict your ability to do something, right? Um, Interaction novelty is what it sounds like. Players may be allowed to negotiate within limited constraints. For example, they may decide to mutually agree on neutral zones where no player may send their piece. Now, this would be interesting, I think, in chess, right? I've never quite seen chess played this way, but it would be interesting to see if we are able to actually interact. And if I'm playing against you and we are relatively well matched, then it might be that we declare neutral zones where we say, okay, I won't send my piece, you don't send your piece. And, what do we do, right? I can sort of imagine interesting things happening. If the players are equally matched, I would say. If one player is obviously not superior, then it doesn't make sense for that player to agree to any kind of neutral zone. Um, event novelty, each player gets an extra move for each time 5 of its pieces are killed. Now, again, you might argue that this is a rule novelty, not an event novelty. So there is still a little bit of vagueness, but we would argue that it's less. The vagueness is less, perhaps, than in the previous hierarchy. And then there's space and time, which were completely ignored in the previous uh, hierarchies because they were thought to be too specific. But in many practical examples, what we found was that time and space are actually really important, and in the real world, also they are very important. And a lot of novelties can be framed that way. Someone is getting extra time, someone is getting no time. There's something in the chess example, right? Like if nothing else has changed, but the board has expanded, as I showed in that visual example earlier on, that seems to be best represented by a space novelty rather than a rule novelty, let's say, right? Or an affordance novelty. So yes, there is still a little bit of a vagueness problem, but we would submit, and not to say this is the best or final way of doing it, but we would submit that the proposed hierarchy has more commonsensical connections to real world ontological phenomena, right, such as time and space. And that's really what we were trying to do, to not get rid of the vagueness problem by becoming more abstract, more prescriptive, but by becoming more commonsensical, so that if you are given a novelty, you can fit it in one of the buckets, fairly evidently. Now, a major challenge, and I'll just stop in a few minutes, is to control for individual novelty types, and an evaluation may be very difficult. So, if I were to ask you that, can your owl react well to object novelty? Can it react well to interaction novelty? One of the issues that arises, if you want to do that, then you would introduce an interaction novelty and not any of the other novelty types, right? That's the ideal, that I want to know, I inject the novelty in one of the types, test the agent, right? Maybe have a range of novelties under a type, test the agent, get the aggregate performance. And now I know, okay, this algorithm can deal well with object novelty. This algorithm can deal well with interaction novelty. In principle, that is possible. In practice, it turns out that introducing individual novelty types can be very difficult. And when you do introduce a novelty, sort of a plausible novelty, an interesting novelty, not something small and artificial, but really something interesting, structural, that would make us think creatively as humans, right? They do tend to involve one or more hierarchy levels. So this makes controlled experimentation a little bit hard. So this was a challenge. And how does the hierarchy link to novelty theories, right? So we can think of the hierarchy as a simpler version of a novelty ontology. And a novelty ontology, what might it contain that the hierarchies presented don't? Now, this, by the way, is a very good research opportunity, because we still don't have, with the hierarchy, you still have a couple of papers at this point, I would say, because of the work by Bolt and so on. But we don't really have a good proposal, even now, for a novelty ontology for open world learning. So we might, here are some ideas, right, for what a novelty ontology might contain that a hierarchy doesn't, which is, meta features such as how often a novelty should be injected in an environment, constraints on which novelties can be combined with others. So this type can be combined with this type should be combined with this type, and so on. Importance annotations of novelty classes with respect to a task environment. So we might imagine that in a war game, these kinds of novelties are more important than these kinds of novelties. In some other environment, in a computer vision task, agent novelties don't even make a whole lot of sense. Rule novelties don't make a lot of sense, but space novelty and object novelties start making more sense, right, and become more important. And links between the domain ontology and the novelty classes and attributes. So there's an ontology for the world, right? So you can think of chess, the rules of chess, the pieces of chess, whether we explicitly state it or not. There is a domain ontology. There is a world model for chess. There is a world model that you can conceptually describe with using an ontological language, right? And there are several candidates for that. Um, how do we have a novelty ontology and a domain ontology and link the two in some principled way? And what's the kind of language we could use to link the two? So the formal language, in other words, So a novelty ontology is ultimately still only a small part of a novelty theory, but this is kind of how they connect. So what Bolt was trying to do was really come up with a novelty theory and or sort of a framework that would give you multiple theories. That's one reason why it was so abstract. Um, the novelty hierarchy that you saw is sort of the other extreme, where it's trying to be as concrete as possible. Uh, but an ontology is in the middle, but sort of a broader framework that takes the hierarchy, takes the ontology, takes the theory, takes the domain ontology, provides all of it in a formal language, and so on, is still, quite ambitious in a way, both in theory and in practice. We don't have a complete environment, I would argue, where we have everything. Like, even if it's a toy environment. So if someone builds a toy environment that has the hierarchy, has the ontology, where multiple theories can be tested, where there is a domain model, and everything can be linked, is still that kind of test bed does not yet exist. So in closing this section, right, do we have good solutions to OWL? Not quite, but there has been much progress in the last 3.5 years. So when we come back from the break, and I hope you don't run away, I will, sort of show you a couple of these events that we have organized and the proposal. So that's my incentive, perhaps, that, if you come back, I will show you the big document, where this problem was described. And other things. Novelty adaptation is much more domain dependent. Novelty detection based more on mathematical approaches like extreme value theory. And there are other resources, but I will definitely show you one when you or two when you come back. And I will just stop here for a break of, I don't know, do we have like how much? 15 minutes. All right. So hopefully we'll see you back at 3:10, but I will just keep the slide on to perhaps, just a summary of some of the things I've already said. So hopefully we'll see you soon again. So, okay, so let me now jump to this question of how do we evaluate open world learning? And some reasons why this is an important and difficult problem. I tried to look for a good reason, and I found this paper that was published in this conference, actually. I believe this was a few years ago. I don't remember when, but this is from this conference, as you can see in the title. And so in the quote, in the abstract itself, what they say is, once a developer tests and debugs the agent with a problem, the never encountered problem becomes the encountered problem. As a result, the problem is solved by the developers to some extent, exploiting their experience rather than the agents. This conflict, as we call the trap of developers' experience, which it's a phrase I've never heard before, but I thought was very interesting, because what it seems to suggest is that you can introduce experience / your knowledge in some way into the development of a system. And in a way, the solution is predestined, right? So the system is not solving the problem, but somehow it's a predestination of sorts. So I think that the evaluation of OWL, right, is a fundamental departure, because the structure of in the usual machine learning, the structure is usually fixed. An assumption that tends to hold even for advanced methods like change point and concept drift. So in concept drift, the statistical distribution could be changing, but the structure is still the same. It's not like a game board where the space is changing, where the rules are changing, etc. Once the structure of the task environment changes, greater demands are placed on generalization. And so in even simpler words, right, if I build the OWL algorithm and also design the novelties, how can I be sure that my algorithm can react to genuinely unanticipated novelty, right? Genuinely unanticipated is really important. Another way is unknown unknowns, right? So you can think about like known unknowns, known knowns. Known knowns are like training data, basically, right? Known unknowns might be like the testing data, because you kind of feel like the distribution you have an estimate of in a way during training, but you don't know which instances you will see from the distribution that you've estimated. But then you have the unknown unknowns. The unknown knowns doesn't really make sense in a way. I mean, it could be implicit knowledge. It doesn't really matter, but unknown unknowns is what you want a true OWL learner to do. So in our nature machine intelligence perspective, we sort of proposed this kind of evaluation paradigm. So what we said was there needs to be a novelty firewall. So the idea is that one team, let's say the red team, generates the novelties and also conducts the evaluation, and the blue team does the development. And the two teams need to be independent. They can communicate, but the communication has to be very limited. They cannot give away the specifics of the novelty. And ideally, you want to give as little as possible, but just enough that you can test for OWL capabilities. Now, once you evaluate, once the algorithm is run, the question is that how do you measure performance, right? And so you want to measure detection, characterization, adaptation. Of these, detection and adaptation, as we will see, are easier to formalize. Characterization, much harder, because what does it mean, right, to characterize a novelty? And I'll sort of present two views on that. Now, in terms of behavior, right, if you look at this diagram in the middle, the red arrows are when novelty is injected. So you're playing the game, let's say, right? And initially, everyone, you're doing very well. Let's say state of the art performance is 90%. So you're winning 90% of the games, let's say, or you're doing computer vision and the accuracy is 90%, etc. Then the novelty gets introduced. And we can sort of see that if we have what we call weak or semi-strong owl. So weak owl is one that can detect, that can only detect. It can't characterize, it can't adapt. The semi-strong can detect and characterize novelty, but doesn't adapt. The strong owl, which is the purple line, can detect, characterize, and adapt. So the strong owl can learn. It can do open world learning. So that's why what you see is that the performance declines for all of them. But the weak and semi-strong owl, I mean, hypothetically, right, if the novelty is challenging enough, we would expect that the weak and semi-strong owl would decline in performance. Then another novelty gets injected, would again decline in performance, would basically keep declining. Whereas the strong owl is learning, so it declines, but then it rises up again. Maybe not to the previous level, right? Because we can probably not expect that once the novelty is injected, that it can learn robustly or well enough as it did in the default environment, where presumably it got many millions of games, for example, to play on. But it does recover reasonably quickly. But what we really want, on which there's very little research, is an anti-fragile owl. So this is still a completely open research area, that how do we build an owl that can actually be anti-fragile? And what we mean by anti-fragile is more than robust. So strong owl would be robust in a way to novelty, right? It's reacting to novelty. Anti-fragile means that it's like the human immune system. So the first time you encounter the disease, it takes you some time, but the next time you encounter a disease or a related disease, you recover faster, right? So what doesn't kill you makes you stronger. That's anti-fragility. What you see here in the pink line is that similar to the strong owl, the anti-fragile owl also gets to the same level, but it gets there quicker, right? It's above the purple line. But and you sort of see the distance, the rate at which it adapts become more and more pronounced compared to the strong owl as it encounters more novelties. So this is kind of what we want, right? We don't have it yet, but this is really what we want, that once the novelties get introduced, you learn, but then as more novelties get introduced, you learn faster, you learn better, right? So how do we do that? I mean, I would say that anti-fragile is sort of an open area, although there is work on strong owl at this point. So a more specific approach, which was proposed in a paper last year by other participants in the Ceylon program, is something like this. So the idea is there's a pre-novelty phase. Let's say you're playing chess, you are winning. The early part where you rise up is kind of your training time. This is the offline. You go, you play the millions of games, you build your agent, and then the novelty gets injected. So that's the red line, the red vertical line. Let's say you drop in performance. The resilience, right, is sort of the difference between the random baseline and sort of the lowest that you're going to see after the novelty is encountered. So in a way, after the novelty, if I'm at 20% and the random baseline is like 5%, then I am sort of 15% more resilient, right, than the random baseline. That I mean, I'm resilient to novelty. I didn't drop all the way to the random baseline, or any baseline that you can think of as having very low performance throughout. Um, the random baseline, by the way, is flat because it doesn't care about novelty. It doesn't care about the task, right? It's just making decisions randomly. So presumably, it's going to do the same on both the novel and non-novel version of the problem. It sees everything randomly. Um, now, after that, the goal would be that the performance, if there is open world learning, then the performance starts rising. And there are two metrics. One is adaptive efficiency, right? So this is kind of like this can be used to measure anti-fragility potentially, right? So if you have higher adaptive efficiency, and also if your adaptive efficiency is rising over time, is increasing over time as you see more novelties, and that would be a measure of anti-fragility. And then there's asymptotic adaptive performance, which is that at the end of a certain number of episodes that you have or games that you have played, um, what's the asymptotic adaptive performance? Now, the word asymptotic is a little bit misleading because it seems to suggest that you're going to play many, many, many games and then we're going to see it at the end. But that's not the true owl problem because we don't want you to play many games, right? So typically we define when the trial ends. So let's say the trial is 40 games, and at some point, let's say the ninth game, you introduce novelty. We might define the asymptotic performance as the average performance between games 35 and 40. Now, if I continue the trial for much longer and you are learning, then you will keep rising, rising, rising. But here this diagram is a little bit misleading in that it suggests that there would be convergence after a while, and then that's what we care about. But you don't want the agent to play too many games. That would not be the sort of true open world learning performance that we are looking to measure. So that's one of the limitations of the approach that they present here, the metric that the asymptotic adaptive performance is the final converged performance post novelty above random. Um, you can sort of think about this as the converged performance of the agent in an environment with no novelty. Uh, the one-shot adaptive performance, on the other hand, right, is the performance of the agent post-novelty after only one episode of interaction with the environment. So this is really what we actually care about. We would want a very good agent to optimize this, right? Which is you see the novelty once, and if you've really understood the principles of the domain, then the argument would be that you should have satisfied right after that. And so what is that performance that you achieve after only one episode of interaction? So this tends to still be very poor. Like when you look at all the state of the art open world learning agents, even now, the one shot adaptive performance is still very bad. Like if the performance drops, they usually need at least a few episodes before they are able to adapt at all. So we still don't have something like this for very challenging novelties. And the NovGrid, in this paper, they also introduced this environment called NovGrid, where it's very interesting environment. So these toy environments are very interesting because they allow you to really play with open world learning concepts at different levels of difficulty, while still being simple enough that there's not a lot of implementation challenge, right? Because these kinds of worlds are not that hard to implement, but they contain very interesting features. So this one, right, it's a grid, as you can see, and the agent is this red arrow, and the goal is to unlock this door. And I think there used to be a video game back in the day that was a lot like this, if I'm remembering correctly, right? There would be where you would have to find the key and unlock the door, and sometimes you would have to navigate the fires and obstacles and so on. This one is much simpler, but originally the yellow key is the one that unlocks the door. And so one example of a novelty would be that now the blue key would unlock the door, right? So in the actual experiment, what they found was that the novelty adaptive agent um, can typically have much more adaptive efficiency. So both of these are learning, but the novelty adaptive one is able to learn much quicker. The non-novelty adaptive agent, takes its time and ultimately has to try lots of things and finally converges on the right solution, but it takes a long time. And this is a very simple problem. So this one is sort of some interesting data. So they used a reinforcement learning kind of approach, which is this PPO baseline. So this is a reinforcement learning, and the door key change novelty. That's what they're showing the result for. So the yellow to the blue, and what you see is that again, the initially the agent is sort of doing some learning before the novelty. The time step is in thousands, but at some point the agent learns a strategy. Of course, it figures out that it needs to go to the yellow key and unlock the door, right? And once it figures that out, the reward is very high. So that's the first climb. Then that's a strategy that is optimal in a way, right? So you see the flattening of the blue line. It's learned a good strategy. Then the novelty gets introduced, and as you might expect, the performance drops very significantly. But it keeps on learning, right? So what you see is that only after 300,000 time steps after the novelty injection, and it doesn't have any special kind of adaptation besides simply continuing to learn, right? So imagine you didn't turn the learning off in the reinforcement learning. If it just continued to learn, once the performance drops, then of course it's going to try to change its strategy if the learning is still on, right? Because you haven't stopped the learning. But it does take 300,000 time steps. So this was a very important experiment. We were really happy that these guys did that, because what they showed was, we often got the question, well, isn't the current approach enough, right? What if you just leave the reinforcement learning running and so on? And what they showed was that in this very simple example, and they showed many more, that this is, a very simple thing. The key is not working. If you were a human, then your first instinct would be the key is not working, so I need to do something different. There's another key. Let me try the other key, right? Maybe that is working, but it takes 300,000 time steps for it to learn that. Now, some of the criticisms, of course, with the evaluation metric here is as I was pointing out, that the convergence, they measure convergence after some arbitrary number of time steps. They don't say that after this many time steps we will measure performance. The other problem is that they don't explicitly measure novelty detection. So in this case, the reinforcement learning kind of can sense that the novelty has occurred because the performance drops. So it's kind of implicit that the novelty occurred, and then it's continuing to learn, right? But in a real situation, what would happen is that you would have learned, then you would have stopped learning. That's kind of what we do, right? So the AlphaGo, for example, it learned Go, but then after that, it stopped learning. It wasn't really, the learning rate, etc., was not, to my knowledge, kept on. If it was, then it was probably very low. So the idea is you learn, then you deploy, right, when you're confident, and then you kind of stop learning with maybe some small probability of changing to some things. And ideally, you would want to detect the novelty if it occurs, and then you would want to restart the learning. You don't want to keep learning, right? So here, they're kind of telling the system that don't ever stop learning. So novelty detection is sort of built into the system in a way, and there's an assumption that the performance drop is the only way to detect novelty. In a lot of cases, that might not be the case. There are novelties called bonus novelties. So this is when, imagine that you're playing like Doom, right, or some video game, and you get a high score, but now I introduce some novelty and you could get an even higher score. Nothing would change in your performance. But if I am more novelty adaptive, and let's say a new entity appears, and let's say I shoot at a new entity in Doom, right? And now my score goes up a lot more. I mean, that's kind of also like a reaction to novelty, right? That you're detecting the novelty, you saw something new appear, then you did something, you explored, you took a risk. And then when you took the risk, you found out that actually there's a much better way of winning the game if the goal is score maximization. So it's not always the case that the performance will drop. It's not always the case that will drop enough. It might drop by a small amount. So novelty detection is not explicitly measured in NovGrid. And in the Sail-On program, the DARPA Sail-On program, they propose a more advanced approach for novelty detection and adaptation that address some of the limitations of the metric. So very similar diagram, right? So again, there's a pre-novelty distribution. Then the idea again is that you only introduce novelty. There's a change in distribution. That's how to see it. So you push the red button. That's what we say. So let's say we're playing the chess, and now there are normal games of chess. I play the game of chess, I get a score, I win or I lose. Then I play another game, then I play another game. So that's happening till n pre. Each game is an episode, what we call an episode. If it's computer vision, then it would be an image that you're classifying, etc. At some point that is unknown to you during the trial, the novelty will get introduced. Um, so the chess board might expand, the agent might behave differently, the pieces move differently, whatever it is. You won't be told that the change has occurred. You'll have to detect it and give a signal if you think that novelty has occurred, right? So it's a 0-1 signal. Um, and then presumably if your performance drops, and in some cases it will, and in others it won't. So when it will, then you hopefully start reacting. The baseline agent will be novelty oblivious. It won't react. The um the if I tell you that a novelty has occurred, so that's the blue line, then hopefully this is a hypothesis that if I tell you that a novelty has occurred, then you will react faster. In practice, it turns out it doesn't make a difference because they still tried, deep learning and other approaches, and it really did make a difference whether they were told or not. Um, the program manager was very unhappy about that because intuitively, it seems like if I tell you that a novelty has occurred in this game, then you would react faster, right? I mean, that's the intuition, but it didn't work out in practice. The black line is that if you are detecting the novelty yourself, and so if you look very closely at the plot, the idea would be that for a while you are not sure, but then you become sure. Let's say at NDT1, that's when you that's when you feel confident enough that there's a novelty. So you give the signal, and then you change something, you switch to some different novelty adaptation, turn on the learning, and then the black line goes up and then it converges. And the reason why you see the asymptotic higher than the original is because to account for the possibility of a bonus novelty. So this is to show that it could be anywhere. It could be below, it could be above, it could be at the previous level. Um, so what are some example metrics that could be used here? So for novelty detection, right, there are two metrics that are important. So one is the number of novel instances that an agent needs to see before it can give the signal. So this would be this NDT1 minus N pre, right? So N pre is unknown. You don't know when I'm giving the novelty, right? So if you need 5 games, right? If you need to play 5 games before you know a novelty has occurred, then the number, this would be like 5. If you need only 1 game, which is the optimal, right? Then it would be 1. So you can sort of see one issue already, that how do we normalize for domains where an episode is really long versus short? Because it seems like the longer an episode is, the more opportunity you have to detect potential novelties, right? So if you just see an image versus you're playing the game, uh, qualitatively it seems different. So you do need to normalize for the domain. This metric, let's say a value of 3, right, might be good in one domain, but really bad in some other domain, right? So this is one issue with this. But a secondary metric is to determine whether the trial is a CDT or a correct detection trial. So did the agent give the signal after the novelty was injected or before? And the reason why it might give a novelty detection before the novelty is injected is because in most games, there is some stochasticity and some probabilistic decision making, right? So in Monopoly, even in chess, right? If the player is being creative, if the other player is being creative, but it's not really a novelty, it's just that they have decided to be creative. That's how they always were. You just didn't see it. Or in Monopoly, you have a dice, right? And you also have cards that you land on the chance and community chest, and you get to pick out a card and something happens. And if you're rolling dice, right, you can never be sure is there a novelty because the statistical distribution of the dice might be off for all you know, and you might think there's a novelty, that the distribution of the dice has changed or the cards has changed, etc. Um, also in partially observed domains, if the domain was partially observed to begin with, uh, we don't know it was the novelty injected or it's just something we haven't seen before, but it's not a novelty. So if there is a false positive, right, then it's a non-CDT. If you give the signal after the novelty is injected, we call it a CDT, and you'll see why this is important in just a moment. And then there's 0-1 novelty detection, which is at the end of the trial. So after the whole thing has come to an end, you ask, okay, was a novelty injected? And it's not as nuanced as the first metric, but it is fair, right? Because uh, at the end of the trial, you're not asking the agent to give you the novelty signal as quickly as possible. You're just saying, okay, I'll give you an entire trial. And now you have to tell me, did I inject novelty or didn't I? Like, just tell me at the end, right? And then we can count a fraction of trials where it correctly detected novelty, where it didn't correctly detect novelty, etc. Now, for novelty reaction, right, an important thing to note is that the metrics for novelty reaction should only be well defined if the trial is a CDT. So conservatively, we may choose not to consider trials that are non-CDTs, but in practice, right, if you have many false positives, if you said there's novelty when there isn't, then and you discount those trials for novelty reaction, that could lead to bias. So in the figure, right, ND minus N3 is, of course, the number of the first metric for novelty detection. At the end of the trial, if you gave a novelty detection signal and there was a novelty, that's 0, 1 novelty detection. For novelty reaction, we could consider the asymptotic performance, right? That is one way. Like, so how would you guys do it? So if you had to measure novelty reaction from a figure like this, what would be some metrics that you would want to consider? Mm-hmm. But are you saying like the area under the curve between the TA2 agent and the baseline, or the entire, or just discount the baseline? So is it between, like, let's say the black line and the orange line, or the black line and the axis? Yeah, and that is not expressed here, right? So that was one of the criticisms, that ideally, if we had the resources, because we are doing such massive evaluation that we didn't have the resources. But ideally, what we would want to do is to take the uh, TA2 agent without the novelty adaptation capability, and then let it learn on its own over time, right? And then to see, like, what's the area under the curve under that situation versus the where you turn on the novelty adaptation in a way, right? So what's the novelty adaptation adding compared to normal learning? And that would have been the ideal, but unfortunately that was not implemented because of resource limitation. The metrics they did consider were the asymptotic performance divided by the baseline. So imagine that at the end of the trial, the baseline achieves like 30% win rate, but the asymptotic performance is 60% win rate. Then this would be like 60 divided by 30, which is like 2. Um, and so the hope would be that that over time this would increase, that the asymptotic performance would increase. But the problem also with the baseline agent that we found, right? Because in theory, this curve looks good. In practice, what we found was that the baseline agent can crash in a lot of cases where, because it's completely novelty oblivious. So if it's not implemented a certain way, then it just won't run, right? When it sees the chessboard has become, certain size, and somewhere in the baseline, it's assuming that the chessboard is the normal 8 by 8 or whatever the size is, then it could crash. And so one of the issues we encountered was that how do we deal with a crashing baseline that is novelty oblivious? So this is like a more engineering challenge, but yeah, whenever you implement something that is novelty oblivious and compare it to something that is not novelty oblivious, the that aspect also has to be controlled for. And metrics for anti-fragility, I think beyond the adaptive efficiency, have not really been defined in the literature. So it would be interesting to, again, like, see whether, what would make for a good metric for that, and what is the how do we build an anti-fragile algorithm? I think maybe folks have ideas on that. I haven't seen anything yet on that, at least to my knowledge. So on that note, can't ChatGPT handle novelty? Now, I do want to show you a demo, but I'll forgo that. What I will tell you is that it gives very glib answers when you give it novelty, and we've done some tests with that. So if we tell it that instead of the checkmating the king, you win the game if you take both rooks. And so how does your strategy change, right? So one very obvious answer is, well, follow most of the general principles, but focus more on the sides of the board and don't expose your rooks too much, right? Normally, you would take a risk with the rooks. You could afford to if it's a powerful play, but now you have to be conservative with the rooks, and the king doesn't matter at all. So you can cease to protect the king because checkmating the king has no value anymore, and the king is not very capable on the board, right? Can hardly move. It's like a pawn. So, um, you know, huh? Yeah. I mean, think about how that changes, right? If I tell you that, okay, checkmating the king is not, will not make you win or lose, then, I mean, the whole view of the game changes, right? Because now it's like, okay, like the queen is still important, but the king is just another pawn, right? Sort of sitting behind the lines. But for the rooks, you now have to be really careful. You have to protect the rook. Um, and probably the best way that someone can attack the rook is through the knight. Now, I haven't thought this through, but I think that if you fortify enough, then the knights become the best attack weapon. So you have to use the knights effectively and then maybe try to take out the other person's knights. If you're, maybe instead of going after the rooks, you go after the knights so that now you're in a stronger position defensively. And then you can try to go after their rooks. Um, but whatever the right answer is, when you actually ask ChatGPT that, it just tells you, okay, here are some strategies for winning chess and just the usual strategies. And then if you try to re-prompt it and say that, well, but this, I've changed this in the game. So don't you think something should change? It kind of realizes it did something wrong. So then it says, oh, I'm sorry. Yeah, you're right. And, now, and what's interesting is it does give the right answer after that. It says that, yes, you should now focus on the side of the board. So I'm kind of divided, that can it handle novelty? I want to say no, but I think that it can be used effectively in an OWL algorithm. I don't think that it can handle novelty all by itself, but it seems to have, if prompted in the right way, it does seem to have some creativity. And maybe it's just a matter of using it to generate creative ideas that can then feed into a proper OWL algorithm. So I don't know, but um, it's not the complete solution to the problem, certainly. And, the point I always like to make with this, especially to audiences that are perhaps, have bought into the hype of the chat GPT, which tend to be, outside computer science, I would say, but there are some, domain sciences, right? For example, that have really been reading all about these large language models, and they are very impressive. There's no question. Um, but there's this view that, oh, they're going to wipe out humanity and this and that, and they're that smart and all that. I'm like, well, maybe they will wipe out humanity, but not because of that reason. Uh, so, and what I try to tell them is that, look, these models have grown bigger and bigger and bigger, but the abilities have not grown exponentially. So it turns out that ChatGPT, I would say, is a different kind of technique. I mean, ironically, it proves the point that you have to combine the training with something else, like reinforcement learning with human feedback, right? That's what made the difference, arguably, with ChatGPT. But even with GPT-3, I mean, there's been work now that shows that if you fine tune GPT-2 in the right way, you can actually get it to perform almost as well as GPT-3 on a broad range of problems. And GPT-2 is much smaller than GPT-3, like 1.5 billion versus 170 billion, much more efficient. Um, so it's clearly what this shows is that not necessarily that bigger is not better, but certainly that even the smaller models, their full capacity is not being exploited yet. So simply making the model statistically bigger is unlikely to lead us to general solutions of to these kind of problems. And so the argument we make, sometimes controversially, is that designing AI for open worlds needs a shift from big statistics to big reasoning. But what do we mean by big reasoning? So I'm not saying that we go back to expert systems and those communities, but we do need a shift from viewing everything as statistical learning to something that is more like that is more reasoning oriented. And the example I give is common sense reasoning. So this is the other problem that is very important in our group. And for a long time, we did not connect common sense to open world learning. We thought they were completely separate problems. We saw common sense more as a natural language problem, question answering, summarization, that kind of thing. But in fact, what we have come to realize is that common sense may in fact underlie, maybe the secret sauce to problems like open world learning, that the reason why we are able to satisfy is because we have common sense. So if from Wikipedia, common sense is sound practical judgment concerning everyday matters or a basic ability to perceive, understand, and judge that is shared by nearly all people. And this is a slide by Yejin Choi from the University of Washington at Seattle. Very big figure in common sense reasoning. And what she said is that, it's really essential, right, for humans to live and interact with each other in a reasonable and safe way. We don't have to say everything because we have common sense. We understand. We understand more than we misunderstand. So the occasional misunderstanding needs to be clarified, but more often than not, it's pretty clear what we are trying to say and do. Essential for AI to understand human needs and actions better. And so it's very irregular, right? So it's okay to keep the closet door open, but it's not okay to keep the fridge door open. But if you want to clean the fridge, then and you've disconnected the fridge, then maybe it is okay to keep the fridge door open, right? So it turns out that it's that almost any common sense rule or knowledge or fact that you can think of, you can add like some more context and the answer would change. And then you add more context and the answer would change or would revert back. So it's very irregular. Common sense is irregular and non-monotonic in that sense, right? So you really do need to understand, every day, what this intangible kind of knowledge and reasoning to work with that kind of context. So research in common sense, of course, has been very intense. Lots of work in NLP and computer vision. Construction of large-scale common sense KBs has been of huge interest in modern AI. So on the right-hand side, you see Psych, that some of you might have heard about from Doug Lennett. This is more than 40 years old now at this point, one of the very first common sense projects back in the day. After that, there was ConceptNet from MIT, still ongoing. ConceptNet is completely open source, so it's very valuable, in fact, to apply that in all kinds of applications. And emergence of large language models has also fueled research in the area. So in fact, both tomorrow and on Sunday, I'm presenting two papers that heavily involve large language models. So if you're interested, do come to those. They're not related to open world learning as much as to common sense. But the large language models has really fueled research in this area. And common sense reasoning has not been properly applied really as a solution to novelty adaptation. So I have yet to see a paper which says that we can apply common sense reasoning to do open world learning. Like that paper is missing. I'm not seeing that. I haven't seen anyone do it or implement it yet, but which is why I say we hypothesize that could be an important work in going from statistics to reasoning. But again, reasoning as in not of the rule-based brittle reasoning kind, because one might argue that ConceptNet and the reasoning, the common sense reasoning, the common sense knowledge itself involves machine learning. To do the common sense reasoning requires a different flavor of machine learning. The common sense knowledge is sometimes derived using machine learning from large language models. So it's not, the key over here is not so much that the reasoning is antithetical to statistics. It's just that there has to be some explicit dependence on reasoning of this kind, whether it's common sense reasoning or other kinds of reasoning. But we simply cannot, wave our wands and say that when the novelty occurs, then I'll just turn the learning back on and the learning rate and the stochastic optimization back on, and it will just learn after 300,000 time steps, right? That we don't want that. We want to do better than that. And, so one reason why perhaps common sense reasoning has not been properly applied as a solution to OWL is that we are still too focused on doing well on common sense problems. So there are lots of question answering benchmarks and common sense benchmarks in vision and NLP. And even now, just like with problems like recommender systems and so on, there's still this focus that I want 1% more, I want 2% more improvement, I want 0.5% more improvement. And there's less work on developing a computational understanding, a theoretical understanding of common sense itself. But there is precedence for that. So, these authors, Gordon and Hobbes actually wrote a book on this called Formal Theory of Common Sense Psychology, where they said that common sense can be divided into background knowledge, common sense sociology, common sense psychology, which I haven't shown all the subcategories for that down below. And they have this very detailed, it reminds me of the novelty hierarchy, right? But it's for the common sense. And what they've said is here are all these different representational areas. And whenever you have a common sense problem, you can actually put it in one or more categories. And in fact, the way they did this was similar to when I asked a question that how would you decide what the different types of novelty are? And I think someone said that you would do a case study and you would look at examples. So in fact, Gordon and Hobbes did that with common sense. They designed some planning problems, very general problems, like planning, not in the computational sense, but like general human endeavor planning problems. Then they gave it to some graduate students, and then they kind of took very detailed notes on how they were solving the problem, what were they doing. So it was kind of like observing and noting down what they were doing, what the process was. And then they kind of tried to distill it into all of these different common sense categories, and then they expanded over time. So it's one of two or three theories out there. I think Gary Marcus has some theoretical work on this, Ernst Davis, and so on. So, I'll skip some of this, but I do want to actually bring you perhaps to, and so, these are all details on their theory, but the key point I want to make is that why this is so useful, and there are these three reasons. So here, for example, within common sense, Gordon and Hobbes bring up these three representational areas that are particularly important. Now, one of them is explanation, the process of generating explanations for effects that have unknown causes. Similarity, the mental process of making comparisons and drawing analogies. And I remember there was someone at the beginning when we did the thought experiments, who used that exact same word, right? Analogies, that somehow you're connecting the novelty to analogies of an appropriate kind and solving the problem. And managing knowledge, right? So concepts of knowledge, belief, assumptions, justifications, and mental processes that manipulate these concepts and reasoning. So how do these relate to OWL, right? So if an agent experiences dissimilarity or regret or violation of expectation, effective OWL may require it to characterize novelty, which can also be framed as an explanation problem. So something goes wrong and your expectation gets violated, or you're experiencing higher rates of regret, so you're not getting the reward that you expect when you make a move. You have to, if you really want to do effective OWL, right, then one would argue you need to, this is an effect, but you don't know what the cause is, right? So you need to figure out what the cause is, which is characterizing novelty. I'm suddenly not doing well because this is happening, or these things are happening, right? So that's the explanation aspect of common sense, how that's relating to this. Similarity comparison, this is directly related to the dissimilarity measure proposed in the framework of BOLT, but we don't know for a given problem and domain what the right dissimilarity measure is. And should we learn it? Should we base it on reasoning? And then on knowledge, knowledge about the world, the way it operates, and of different types of novelties the agent has encountered before, especially in a continuous learning setting, are critical for the other two features, right? So whether we're talking transfer learning or some other kind of learning, unless you have the right knowledge and the concepts of knowledge and you know what to transfer and what to revise, right? You won't be able to do effective OWL. So, it turns out, I suspect that when we go through the other common sense representational areas, we can also find analogs to OWL. So this is just, one example of, kind of reasoning that, I'll skip this, of the kind of reasoning that can presumably lead to faster, better OWL, right? But again, we haven't seen the papers on that. So it's a promising research direction. So, I want to just spend the last couple of segments to show you an example novelty generation system. In fact, I'll show you 2 or 3, but I'll go into one in detail, which is really our system. So we know everything that is going on inside that system. But there are a couple more that have been published that I will also allude to. So this was the system that we built in response to the DARPA effort. And so there is a code base for this. We are cleaning up the code base now that the program has ended. So we'll have a production level version of this hopefully in a few months, but there's already a code base available. That has been getting updated for a few years now. And there's this reference which describes the generator in a lot of detail and was published in Simulation Modeling Practice and Theory. So basically what you see at the top is the world model, right? So that's the normal game. These are all the elements in the normal game. We implement those as classes, right, in subclasses. So it's an object-oriented programming framework. But what we do in order to make it suitable for novelty generation is that we have a way of changing any function and any parameter we want through reflection. So we have written the code in such a way that everything almost is functionalized. So basically you can swap out a function for another function, right? And so functions are really functionals. That's the way to think about it, that we can replace the default function with another function pretty much anywhere in the code. And so for this reason, you can change the code in all kinds of ways without breaking the syntax, right? Because syntactically, the name of the function is still the same. When the agent is calling different functions and is playing the game, it's not really seeing any syntactic difference. So it doesn't break, right? So the agent can play the game without breaking, even the novel game, but the logic inside the function might be different. So you might get unexpected causes, effects or violation of expectation. And the question is that you as an agent, are you able to figure out that something is going wrong, something is being violated, there's something happening in the game that should not be happening, but you can't make out syntactically. So in that sense, it's very different from a game where you can visually perhaps see, right? Like something has changed, the board has expanded or a color is different. And this is an abstract game board. So you can't really see that something has changed. You cannot really syntactically see that something has changed either. So the only way that you can really detect novelty, which makes this interesting, is by very carefully observing the gameplay. So as you're playing the game and taking actions and seeing what's happening, what the cache levels are and who owns what properties and who's making what moves, you have to really see whether there's a violation of expectation by looking at the gameplay really, right? So the novelty detection is quite challenging. Even the best systems, after 3 or 4 years, were only able to do like 30-40% novelty detection. Even though as a human, we can make out the novelty quite evidently. So at an API level, right, this is kind of how it works, where we kind of avoided, race conditions in the code by having these phases. So you would have like a pre-roll phase where you could make decisions to interact with an agent, before the dice is rolled. Then after the dice is rolled, you have another phase, then you have another phase. And in all cases, the agent, which is the agent has to implement decisions for these 6 things that you see over here. So make pre-roll move, make out of turn move. So these APIs are released to the agent. What we tell the TA2 agent, the agents that are implementing the game playing, that these are the functions you have to implement. So whatever the logic is, right, this is where it has to go. And, the overall interface will prompt you, right? So it will call the make pre-roll function and then will give you the current state of the game board, will give you the relevant information. And now you make your pre-roll move and you'll get to observe the effects. And now you get to decide, is there novelty? Is there not novelty? If you believe there is, then send us a signal, right? We'll show you everything that you would expect to see in a Monopoly game. You would see the cash levels of the other players. You'll see who owns what. You'll see all of those things. And so this is kind of how we implemented this to avoid syntactic problems and race conditions. And again, similar to the Nov grid, what we found is that novelty in the environment does hurt performance, and open world learning does help. So what you're seeing here are 2 agents, A1 and A2, and A2, the novelty adaptive version of A2. And if you look at the columns, right, there are some novelties like protected colors. That's the example I showed, right, where some colors are now rent protected. And indeed, you can see that if you, the A2 pre-novelty actually is not doing so well. It's only 25% win ratio. But in post-novelty, right, when it's novelty adaptive, it's able to take advantage of the fact that protected colors should not be purchased. Uh, and you should spend money on other properties because protected colors are worthless, right, in terms of their rent potential. And you can sort of see that sometimes the differences are quite big. Um, other times what is interesting is that the mortgage de-evaluation in that novelty, the post-novelty is worse than the post-novelty is, you know, doesn't make any difference, when it's adaptive. Um, the reason why, and in yet other cases, it can even decline. So the extended locations, right, the A2 post-novelty non-adaptive is actually higher than the A2 post-novelty novelty adaptive, right? So it's even in cases where you might feel like it's doing well and it's adapting to the novelty. This is all very good. What is so interesting is that there are other novelties where it might be coming at the price of doing badly on other novelties. So you have to test on a broad range of novelties for that reason, because you can do well on some, but then you might do badly on others. And so statistically, you may not really have a difference, when you aggregate, right? So does it have a good open world learning performance? Yes, if you look at some novelties, but on others, it can actually decline in performance. So just a couple of video demonstrations to make this sort of a little bit fun, and they both playing together. I do apologize for that, but can anyone tell me, just based on this, what the novelties are? Both of these are novel. What's the most obvious difference? Okay, so in the default game, you have two dices. So the right one has only one dice. So that's novel. What about the left-hand side? What's novel in that one? Exactly, right? Which one do you think would be harder for an AI agent to adapt to? From the default, let's say you've trained on the default and maybe you have some owl in there, some kind of learning. Like, which one do you think would be like more, like higher order adaptation would be required in a way, like more reasoning based? Everyone says that, and it turns out they're actually wrong. So, huh? So I'll tell you why, and it will make sense once I tell you. So but let's say I tell you it's the right one. Can you think of a good reason why the right one might require a more fundamental shift in how you look at the game? There you go. That is exactly right. And why does that matter? Well, like, what's the rule in Monopoly that makes that very important? Well, yes, but there's something else, which is that when you pass Go, you get $200. Now it's going to be halved, right? The pace will be halved. And the probability that you will land on, like if I spend a lot of money and monopolize and someone doesn't land, right? Then it turns out, so there are a couple of interesting things. So let's say I land on 6, which is like the light blue property. Um, with a single dice, right? There's a higher probability that I could land on 8 and 9 than with a multiple dice. So in a clustered property, usually what happens is that if you land on one of them, then the probability that you will land on the other one in the group becomes much smaller, because with two dices you get bigger numbers, right? So if you like divide, the probability of getting 2, right, is you have to get like a 1 and 1 on the two dice, right? Which is like 1 divided by, I guess, 36 or something like that. Like it's a much lower probability, but on the single dice, it would be like 1 divided by 6, right? And for 3 would be like 1 divided by 6. So it turns out when you work out the probabilities, the clustering can actually play a much more important role also. But most important is the pace that is the problem. So you have to manage your cash very carefully. That's the consequence. So when you're going around the board, you have to be very careful about purchase decisions. You should not purchase every property you land on, which you can afford to do in the default game, at least for the first few rounds. Um, here you have to be much more mindful. In fact, we have observed that a pretty good strategy might be to make to to have like some properties that you would absolutely purchase and to not purchase others, at least on the first 1 or 2 rounds. So if you land on a railroad, purchase that. If you land on Boardwalk in Park Place or the green properties, purchase that, but avoid purchasing everything else before the yellow properties, except railroads. So it turns out if you do that, you have a higher chance of winning against many players. The left-hand side, if you think about it, there's really nothing you can do, right? It doesn't change anything fundamental about the strategy. It might change the rate at which you observe a win. There is some chance that it will take more time for you to win or less time for you to win. But fundamentally, there's really nothing about the strategy itself that you would change. You would continue to purchase the blue properties. If your agent has done something really dumb or has internalized something really dumb, like saying that, okay, buy properties at the end of the board, which are more expensive, right? So if it's learned a pattern like that, then you can imagine that yes, it will do badly. But typically, most state-of-the-art agents will not be that dumb, right? They will kind of associate more with the name of the property and the value of the property than with the position in the board, which is a much weaker feature, right? So there is some chance that if you don't react and you've learned something bad in the default game, that you could still suffer. But most of the time, it turns out that even if you do nothing, like you don't adapt, if you have a very good strategy to begin with, you would still do okay in the first version. But in the second version, you would still win, but it would go down. The win ratio would go down if you don't account for the slower pace at which your cash gets replenished. Um, so yeah. Okay, so another example is Angry Birds. So this was developed by a team at ANU, Australian National University. And this was a very interesting domain because it tests an agent's owl abilities on a task grounded in physical reasoning principles, which seems strange. Why would there be physical reasoning in this kind of game? But the reason is that the Angry Birds is a very physical game, right? Like you really have to hit the pigs in the and you have to kind of figure out what the right angle. And I've never played the game, but my understanding is that you have to have an intuitive understanding of physics, right, to do well on the game. It's really not an intellectual game. It's more like dexterous, I guess, perhaps is like the word, right? You have to be a little bit physically dexterous and have like good aim and good angles and things like that. And what was interesting was that they kind of proposed they said that the Angry Bird is a very good way of measuring what they call the physical reasoning quotient or the FIQ that reflects the physical reasoning intelligence of an agent, which I thought was very interesting. It's a different way of evaluating an agent. And the second aspect, which is learning agents, even with good local generalization, struggle to learn the underlying physical reasoning rules and fail to generalize broadly. So again, I think that in this case, right, what they are really saying is that again, you have to go from statistics to reasoning, but here the reasoning are physics reasoning. Now, whether you use Newtonian equations of motion or you're learning a model of physics from the game, and then you're applying that when you encounter a novelty, uh, that's up to your agent. But the key aspect is that you must have a fundamental ability to understand the physical reasoning rules. I mean, think about it this way, right? Imagine that the bullet is, let's say that I'm shooting at a flying pig and the bullet becomes very slow, right? So I'm playing the game and all of a sudden I see that that sling or whatever that I'm shooting at the green pig has become very slow. Well, what would I do, right? It's not that I need some statistical learning. I mean, I would kind of figure out that, look, either I have to anticipate where I have to change my anticipation of where the pig would be after certain number of time steps, which is higher, right? So this could be the case if I see that the trajectory of the pig is very predictable, right? So the pig is not seeing the bullet and changing the trajectory, then I can do that. But if the pig is changing the trajectory when it sees my bullet, then the only way to do this is to get closer to the pig, perhaps, right? Or something like that. That if you get closer to the pig, then you're in the situation as before, that before it can change, uh, you can hit it, right? When you're much closer. So I mean, if we think about it from a physics standpoint, what we're really saying is that because the speed has gone down, right, the time has gone up, right, for the same distance. So if you if the time matters, right? If the pig's ability to move trajectory is dependent somehow on the amount of time it takes for a bullet to reach the pig, then you have to minimize the distance, right? To bring it back on track. So that's a physics reasoning principle. We do it very intuitively. The AI does not have to do it intuitively, but it needs to apply physical reasoning rules to be able to do this. If we wait like 1,000 games before it can learn that in some black box fashion, that's really not what the goal here is, right? Yet another example is smart environments from Washington State University. So this is called SHGAN, and this was meant as a test bed for structural novelty detection in the smart home. So they use this GAN to replicate sensor data that you would see in a real environment. So they in fact showed that sensors in a real home, the measurements are very similar to that generated by their GAN. And so they can use the GAN to evaluate OWL, right? Because if you think about your ring or the doorbell, right? Like all kind of things can happen. There may be an intruder that comes to your house in the middle of the night and triggers the ring. Now, on the other hand, if you know that a lot of construction is going on around your house, that you won't be triggered by the ring. You know that there's going to be a lot of alarms or a lot of notifications on your phone, right? So to the AI, that's all just going to be sensor data. So can we kind of figure out what is actually novelty detection versus not, right? Okay, so closing out, and then we can just stop for a last round of Q&A. So research opportunities, which, some of you might be interested in. So one of the questions that we have struggled with a lot, in the program, and I think this is very interesting, both from a theoretical standpoint and also from a practical standpoint, is what makes some novelties more difficult than others, right? So one might say that if you have a higher dissimilarity, then maybe that novelty is more difficult. But we found that it can really depend on the dissimilarity measure. We haven't really found a global dissimilarity measure for that can work, that can predict the difficulty of the novelty for all the novelties. So what we have found, in fact, is that some novelties are generally more difficult for almost any agent if the domain is sufficiently complex in real world. But for other novelties, there could be agent dependency. So it depends on the agent. If it's a reinforcement learning, then some novelties will be hard, but those same novelties may not be hard for a different kind of agent. But these are like less interesting. I mean, of course, in practice, the second question is also interesting if you're trying to understand the algorithm, right? So if you want to understand what makes reinforcement learning trip or what makes a probabilistic model trip, then you want to study the second question. But the first question, I think, is more fundamental, which is that what makes some novelties more difficult than others? I don't think it's arbitrary. There should be, it should be more predict, even before you run the system. Here's one way to think about it. I give you a system. Maybe I even tell you everything you need to know about the system. I tell you what it's been trained on. I tell you what the architecture is, how many parameters it has. You can think of a system like that, let's say. And now I give you novelties. And what you have to predict is, without running the system, what will the impact of the novelty on the system be? How do we do that? That's kind of what this problem is coming to, right? And so maybe you'll be able to measure the dissimilarity, and that's where the predictive power will come. But the experiments have shown that there's a lot to be desired from that. It's not as predictive as we would have liked for. And for agent-based domains, for action-based domains, it's very difficult to define dissimilarity functions to begin with. So, here's an example from a game theoretic domain that we apply to study this problem. So many of you have probably heard about a prisoner's dilemma. We ran an iterated prisoner's dilemma, which is a classic game theoretic tournament. And we implemented these 20 novelties. And we also implemented about 20, 30 agents. These are agents that are well known in the literature, in the game theory, tit for tat, random, always cooperates, always defects, etc. So there are like 20, 30 agents that were in the literature. So we implemented all of them. We implemented 20 novelties. Then we ran each novelty on all the agents and then averaged and showed the performance with the arrow bars over here. And what you indeed find is that there are some novelties, right, that generally speaking, all the agents find difficult. Yes, there are some big error bars, but even if you take the error bars into account, some novelties are really easy. others are in the middle, others are kind of, really hard, right? And even with the arrow bars. So what this showed us was that even in a relatively simple domain, such as iterative prisoner's dilemma and established agents from the literature at different degrees of complexity, we still find that there's something about a novelty that seems to be agent independent. Some novelties are harder than others. And we don't really have a good theory why some novelties are harder than others in a given domain. Um, how do we evaluate an agent's ability to characterize novelty? Now, this is a very interesting problem, one that we underestimated. So you might think that characterize might mean to imply effectively describe, right? But the problem here is that we want to test an agent's internal ability to characterize novelty, not the agent's ability to describe the novelty to us, right? I mean, one way to think about this is the agent may have characterized the novelty in its own internal computational machine learning language, right? It may not be able to describe it to us in our language, right? The but then you might imagine that now, right, what some people are saying is that, look, that may have been a problem before, but given the large language models, there is no excuse for the agent not to be able to describe the novelty to us in plain language, if indeed it has understood the critical features of the novelty correctly. And so this is somewhat similar to the agent being able to explain itself, right? I mean, it's how we evaluate explanation, if you think about it. So maybe we evaluate novelty characterization the same way we evaluate explainability in AI. That's one view. Another view is that maybe we don't need to go into all of that. What if we just implement novelties where we are sure that unless you have understood the novelty, unless you have characterized the novelty, it is impossible for you to react to it. So you cannot get good reaction through accident. If you don't understand the novelty and do something random or don't do anything at all or just try something, you'll fail. So you might imagine that the one where the bullet becomes slow in the Angry Birds, and that one is sort of, maybe you do need to understand that the bullet has slowed, and that's the novelty. And that if you understand that, then you would realize that, okay, you need to go closer to the pig, or you need to look for pigs that have predictable trajectory, that don't see the bullet coming. And if you don't understand it, you would randomly shoot, right? And it's slow and the pigs would avoid it and it would go nowhere, right? Or you would just shoot at the pig, but it's too slow and the pig would avoid it. So what Johan, the Angry Birds PI, who took the second view, he was a very strong proponent of the second view. He would have said, well, yes, the first type where the pigs are like blind to the speed of the bullet and don't see the bullet coming, so they don't change the trajectory, um, would not be a novelty that allows you to characterize, because it's possible that you shoot at the pig is not changing its trajectory, so you hit the pig, and even without understanding the novelty, as long as I'm aiming correctly, once in a while I'll get the right shot and I may still end up passing the level, right? But if the pig can see the bullet coming, and you might imagine that if the bullet is greater than 2 time steps from hitting the pig, then it can change the trajectory. Then that, you might imagine, would require you to characterize, right? Because you would shoot the pig, that's what you would try to do. Uh, One might imagine that the game is challenging enough that you would not be close by, you would be far away from the pig, and then you would deliberately have to come closer. Simply shooting more arrows or bullets or changing something else will not help you. The only real way to do this properly is to go closer, right? And shoot the pigs closer. So you have to use your time to go closer to pigs that are hopefully closest to you, and then try to sling them, right? And so if you have characterized novelty correctly, then especially in a time constrained game, you would do that, right? You would use the time to get closer to the pig and then shoot the pig. Um, and so the second view is somewhat like that, where you are basically saying that if you have succeeded on the task, that is evidence of novelty characterization, that we have designed the novelty in such a way that solving for it is evidence that you have understood the novelty. Otherwise, you would not be able to succeed on the task. But not all novelties are like that, right? So you're kind of discounting a big set of novelties away in order to test that. So agent's failure or success to perform well is a proxy for its ability to characterize and, more loosely speaking, understanding novelty. So this is the second view. Another research problem is that how do we automatically generate novelties at varying levels of difficulty? So this is a paper that we are writing now. We have just about finished the experiments and we are writing this up. So I just wanted to sort of show this to you. So we are defining the problem differently here. So rather than saying that the algorithm has to do open world learning and adapt to novelty, we are taking another different view in this, where we're saying that, okay, imagine you have an agent A, right? You see that on the left-hand side. The agent A has been trained. We want it to be robust. We want it to hold up well when novelties occur, but we are not requiring it to do open world learning. Okay, so it's a trained agent. We'll deploy it on Mars. Let's say it's a rover. We'll send it to Mars. It will not do any learning on Mars, but we do want to make sure that if it encounters a novelty on Mars, that it will be robust. It won't just fail and drop dead, but it will be able to do something. It will be able to react in some way, or it will be able to do something decent, maybe hunker down, maybe wait for the storm to pass, whatever it is, right? Do something reasonable. So we want to know that what are the novelties that will have the greatest negative impact on the agent, right? So what will make the agent fail? So we are not saying that we inject the failure and what will make the agent learn or succeed. We are instead asking that given an agent that has been trained in a rich environment, what are the novelties within the environment that will make the agent fail? What are the blind spots? It's kind of like doing unit testing, right? So the bug testing or the deployment testing, right? What are the structural changes in the environment that will make the agent fail? And we don't want to perturb the environment randomly. So our thesis here is that let's have these novelty primitives. So these are like atomic changes, right? So you change the color of a property, you change the wind speed, you change the other things. These are like primitives, right? They are roughly atomic changes. Roughly sort of changes that stand by themselves. You can't break them up any further, right? So given a set of primitives, we can sort of think of a novelty as a combination of primitives, right? So you change the wind speed and the storm clouds are coming and the soil is breaking under you, right, on Mars, and so on. So 3 or 4 things might occur. They are most likely correlated, but the idea is that if you have a novelty that is the combination of several primitives, like which can be efficiently find the combinations that will have the most negative impact. And computationally, this is an interesting problem because if you think about it, there's a exponential number of combinations, right? So if I give you 100 primitives, then, and even if I limit to, let's say that a novelty can only have at most 5 primitives. Suppose I make that restriction, that reasonable constraint, that's still, like basically that is like, it's like 100 to the 5 or something like that, right? Number of combinations approximately. So it's kind of exponential. And so what we are saying is, can we do an automatic novelty search? Like what's an algorithm, a meta learning, right? That can actually look at the space of primitives, collects data wisely, right? So maybe the automatic novelty search tries some primitives out, right? One by one, collects individual data. So let's say I try out all 100 primitives. I see what the effect is on my algorithm, on my agent. I get a profile. I get the expected performance for each of the 100 primitives. That's just O of 100. So it's relatively constant. And then I try to profile in some way. If I combine this primitive with this primitive, then this is the expected performance. And this is the function that will best predict what will happen to my agent if I combine this with this with this. And so it's almost like you're trying to learn the impact of the novelties when you combine the primitives in some arbitrary order. And then on the basis of that, you can like predict that, okay, if I combine this, this, and this primitive, that will have the most negative impact. If I combine this, this, and this primitive, that will have the most negative impact. And we can evaluate algorithms pretty efficiently because it's a search problem. So you can actually apply almost any search algorithm to this as a baseline. And the question is that your meta learning, is that doing better than, let's say, a breadth first search or even a linear regression over the individual primitives? Yeah. not in the first paper, but I think that would be a very promising direction, especially in domains where the common sense and theory of mind play a very important role. So if you have a second person that you're interacting with, like in that kind of domain, like maybe you're conducting a negotiation and you set up the problem where there's an agent and the agent is conducting a negotiation with an artificial agent. And maybe it's like diplomacy, perhaps, right? The game of diplomacy might be a very good example where theory of mind and common sense could be very interesting ways to generate good novelties, and also interesting for solving the novelties, but certainly very good for figuring out what might be good novelties for a given agent. Um, right. So yeah, well, maybe you'll write a paper on that. So yeah. Yeah. So budget is basically how many novelties are you allowed to try out before you have to give your answer or your best. So what we ask the algorithm is that give me the novelty, or which again is a combination of primitives. So it's a set of primitives like that you believe would have the most impact. And the budget is how many primitives you're allowed to try out to make that estimate. So ideally you would want the budget to be like the 100 to the 5, because then you can just try everything out and just return the one that has the most impact, right? But you won't get 100 to the 5 budget. So you might get something like, let's say, a budget of 600. If you get a budget of 600 and there are 100 primitives and 100 to the 5 potential combinations, then the question is, how do you use that budget to build a model um, that can give you the best novelty estimate? And what's also interesting is that even after you build the model, you may not want to use the model entirely for prediction. You also want to save some of the model to validate your prediction, because, right? And yeah, so the budget is a very important factor, because certainly for some of the deep learning, meta learning based approach, like if we've also used the reinforcement learning as a meta learning for this problem, but the reinforcement learning is data hungry, obviously. So we don't want to bias anything in favor of it. So for something like breadth first search or even greedy algorithm, um, they can work with a budget very effectively, but they are obviously more local. So in part, we think that even the definition of this problem actually was the main contribution in this paper, because we're saying that the approaches, are really not the thing that we want to draw attention to. Instead, we're saying that if you want to really test an algorithm that is meant to be deployed in the real world, then this is a way in which you should test the algorithm with this budget and try to find the novelties that will have most impact. And you should not try to second guess and come up with those yourself. Instead, the proper way to do it is to define the primitives. So there is some knowledge. It's not completely like the novelty firewall, because you're aware of the primitives. Ideally, you would want to develop the primitives after you have done the algorithm. But even if you haven't, that's still okay. As long as you have a rich set of primitives, we argue that it's better than the current practice where you're really, doing some kind of stress testing, but not structural stress testing. So we're saying this is at least one step above that you may still leak developer knowledge, but you're doing some more structural stress testing than you were before. Then if you have enough primitives, then the chances of bias goes down if you apply a good search algorithm, because the sum of the primitives, it's difficult to argue that you can leak knowledge of like 100 to the 5 potential novelties into the system, or even 100 potential novelties into the system. So if you define an expressive set of primitives, then the threat of leaking developers' knowledge goes down as well. Yeah, that's where the budget comes in, right? So in this framework, we actually did not go further. We felt that using the novelty hierarchy would be controversial. So we just frame them as primitives. Like the some of the primitives are more agent based, some of them are more interaction based, and so on. But we didn't formally like argue for the hierarchy being used in this particular work. But I can imagine that this can be made even more rigorous by saying that, okay, here are 20 primitives for action, here are 20 primitives for interaction, 20 primitives for space, and so on. And so let's have primitives for each of the levels of the hierarchy. I think one of the values of doing that is that it allows you to be more confident that you have designed diverse primitives. So the hierarchy would play a more pragmatic role, where it's like, well, we're not claiming these are all the novelties, these are mutually exclusive novelties or anything like that. But because we have implemented primitives in all of the different categories or subtypes of the novelty hierarchy, we will likely have a more diverse and challenging set of novelties and so we are doing more structural stress testing in a way. Parameters. Yeah. Exactly. Yeah, in the paper, we call these instantiated primitives. So basically, uh, I it's like let's say you have a primitive, like changing the color of a property in Monopoly might be a primitive, and then instantiating it would mean that you send the property and the new color as arguments, and so there are many different combinations of that, right? And so conceptually the tree is treating each of those as a separate node. Now, if you have real numbers, then we discretize them so that we get a finite tree, even though it might be very big. But if you have like, let's say 40 properties in Monopoly, and there are like 6 different colors that each one of them could potentially be changed to, then roughly speaking, right, that's like 40 times 6. And so a single primitive leads actually to 40 instantiated primitives. And so very quickly you can have thousands of primitives, which is not a problem at all because it's still a very manageable space to navigate. Of course, you can't materialize the trees. But it's a manageable search problem in the sense that it can fit in the individual primitives can all fit in memory. So it's still a manageable search problem, but the search becomes computationally explosive very quickly. Yeah. So just to close out, and I know we're out of time. So open world AI research, I would really say requires bridging principles from engineering and science. And so the reason why I say that is the evaluation, if you think about it, is really very sort of a new kind of science, right? It's saying that we have to think about this almost like a drug trial. It's not quite a drug trial, but it's similar. It requires a similar kind of blindness and firewalling and metrics computations that try to mitigate bias as much as possible. But the engineering challenge is also very significant. And I don't know about a dose of philosophy, but just as a olive branch, right? It probably would not hurt, but I would not say that that's the fundamental ingredient. Now, open world learning has many applications and benefits for humanity. So these are 3 that we point out in our article. But one of them, of course, is self-driving cars. And this is inspired by real examples. Imagine that the car is approaching an intersection and there are 2 traffic lights and both of them turn green. This can happen. So there's a cyber attack that actually it's possible to do that, it turns out, where both the lights can turn green. And if you're approaching the intersection, I mean, you're in a real dilemma, right? And it depends really on the context of what you should do. So of course, there are situations which are lose-lose, that no matter what you do, there will be an accident and someone will get hurt and you can only minimize. But there are also situations where it's possible to avoid damage. So if there is a car speeding behind you, and you don't see any cars coming in the intersection in front, then you should actually cross the green light. You should not stop, right? Because you should start slowing down, but you should not jam on the brakes because there's a car behind you and there's no one in front. So you would presumably avoid damage by doing that. However, if there is no one behind you, or whoever's behind you is far away enough, but you see that there's a person crossing or that there are cars crossing, then you should jam on the brakes, slam on the brakes, right? I mean, that's the right thing to do in that situation, and hopefully everything will be fine, and so on, right? So it's kind of, this is, at the very least, right? If you have weak owls, if you can only detect novelty, then it would see that the traffic light is different than what I've seen before. If it can characterize, it would say all lights are green. The intersection is not safe to enter. And if it's reacting, again, there are different solutions, but one solution might be I'm going to stop, turn on my my hazards and alert a human, right? Assuming this is the right thing to do in this situation. Another example that we are very interested in, and a very real example, is healthcare. So a lot of times, the healthcare, I mean, of course, with COVID and some other diseases, it's very sudden. right, when something changes. But there are many emerging diseases. There are also, diseases like measles, right, where the vaccination can wane over time. So in the UK, I remember reading about that there was a possibility of a measles epidemic in the 90s. Now, a lot of people thought that something like measles has been eradicated in the developed world, right, because everyone is vaccinated pretty much. But it turns out that some kids, there was a rising percentage of children who were not being vaccinated against measles. And as we now know from the COVID, and hopefully a lot of us now know, but epidemiologists are very familiar with the concept of herd immunity. So if you don't have herd immunity, then there could be an epidemic. Basically, once you achieve herd immunity in the population, so if that's 86%, then that would mean that if 86% of the population is vaccinated or immune, then you can avoid the epidemic. It doesn't mean the case would go to zero, but you would avoid an epidemic of sorts. It wouldn't just grow, very quickly. So the UK had actually lost herd immunity for measles in the 90s. And the epidemiologists fortunately saw this in the antibodies in time, in the seroprevalence surveys and so on that they were getting from hospitals. And they devised a strategy and they have pushed for a big vaccination campaign. And luckily, there was no epidemic. There was no outbreak. They were able to get the population vaccinated enough that they were able to avoid the outbreak. But it happened slowly, right? I mean, it's not like 1 year, suddenly everyone stops deciding to do a measles vaccination. I mean, maybe if you find out it's unsafe, then you might stop all of a sudden. But usually, it's like a slow trend, right? And a lot of medical problems, diabetes, etc. Many problems are of a slow nature, chronic diseases. So it could be that there's a biopsy, right, which is unusual. The traditional AI would just say good prognosis, bad prognosis. But the OWL AI would maybe see that, okay, this image is different than images. So it's not just good or bad, it's just different, right? So this is kind of like open set recognition, not a very new problem, anomaly detection. You might think of it that way. But the characterization is that this is a novel combination of staining and histological features, more detail, right? And then the reaction would be that based on staining signature, this has a bad prognosis. Based on histological features, this has a good prognosis, confirmed with human. This is really what we want, right? I mean, ideally, we would want the machine to look at an image like this and be able to give it to the human and ask the human that, okay, this is what I'm seeing. According to this, it's good. According to this, is bad. So what is it and why? Again, there's some reasoning involved here, right? Whether we call it common sense reasoning, domain specific reasoning, but there is some kind of reasoning. It's not just statistical. And then cybersecurity, right? So imagine you send a phishing email, an attacker sends a phishing email to the user, and the AI, right? Maybe it's not, it's reading your emails. It's not really surveillance. I mean, usually corporate emails are anyways subject to surveillance. So let's say this is a corporate email, and this is a signature of emails I haven't seen before. This may be a novel type of phishing attack. And then the reaction might be that, okay, I'm going to temporarily block these emails from going through the company and alert IT, or I'm going to disable links and alert IT, or I'm going to put a message on the email, etc. Right? I mean, as we've all seen, the current systems are not very good at doing this. The spam filters are still not that good, I would say, in many servers. And there's a lot of phishing attacks that continue to happen that bypass a lot of the usual, security measures. So if you're interested more, there's a lot of communities and resources. I especially encourage the triple AI. It says upcoming, but it happened in 2022. So this slide is from early 2022 in a way. So the spring symposium, let me see. It's not well. The link I'll share the slides, but basically the link was there in one of the other slides. But if you just search for designing AI for open worlds, triple AI spring symposium, you'll see the webpage. It's on our group webpage, and of course, there are some other links here as well. Based on our work in the program, we wrote a number of press articles actually on this, and it kind of explains it simply why this is important. And with that, I will actually just end with maybe this slide over here. So that brings us to a halt. All right, questions. Oh, thank you. Oh, sure. Yes. So let me take the second question first. So I think that that is one of the challenges, right? Because the so coming back to the monopoly example, it's quite possible that I will observe, two sixes like 3 or 4 times in a row. It is statistically possible. And in these evaluations, we are running many hundreds or thousands of games. So we will see, the gambler's fallacy play out, right? And so the gambler's fallacy is that that probability has no memory. So, you like, let's say that you get, you're tossing a coin and you get 3 heads in a row, and then you might think, well, I got 3 heads in a row, so the next one is going to be a tail, right? But that's a fallacy because probability has no memory, right? So it's possible and in fact likely that you will see outliers, and the outliers are not really novelties in the sense we have described them. They are just unlikely values from the pre-novelty distribution. So you might want to adapt a different strategy for outliers, but they are not really novelty. Um, I think with novelty, there are big structural changes. So the distribution itself might change, the objects in environment might change. And so it's not really an outlier, it's a different distribution is the correct way to think about it. Or a distribution with different parameters, right? Which is a different distribution. So it's a distributional change, not just a sampling, an unlikely sample from the existing distribution. So yeah. Yes, and I think that that's why it can be controversial to um, I mean, it could be that what we think is a false positive, novelty detection, is not really a false positive. And I think that's the reason why uh, the novelty detection metric should be taken with a grain of salt. The true metric is novelty characterization, because if it says that I detected a novelty because the player seems to be taking a lot more time, and the average time in the pre-novelty was this that I observed, and now the new time is this, and it's significantly different. Well, it's possible that in the underlying distribution, that time is the slow time is possible, but given this reasoning, it's hard to argue against the reasoning. It seems like it's a correct characterization in a way, right? It might be subjective to rate that as right or wrong, so you have to have very clear guidelines on how you would evaluate that. But this kind of shows you that evaluating novelty detection and characterization can be challenging because you can conflate it with unlikely samples from the underlying distribution, and something you have to keep in mind. So what we recommend is that when you're evaluating, you have to pick novelties that are really and truly structurally different. Um, and yeah, and over a big enough set of evaluations, it would still average out. So even if you do see an unlikely sample and you rate it as a novelty, sure, you won't get a perfect score, but few samples like that are usually acceptable as long as you have a big enough set of samples to begin with, instances on which you inject novelty and don't inject novelty. um yeah. No, I understand what you're saying. So the way I would argue for that is that the agent, the other agent, the adversarial agent attacking by injecting novelties into the environment is itself a kind of novelty, right? Because you might imagine that you expected the adversarial agent to do certain things, but instead the adversarial agent is trying to trick you by injecting novelties into the environment, or putting distractors into the environment. So I would say that this is like an agent novelty in a way, but it's a very difficult agent novelty because it's what one might call a second order novelty, where there's a novelty that in turn is spawning other novelties. And so in trying to adjust to the first order novelties, you're missing the second order novelty. So this would be a very hard problem, I think, to solve, because even solving for the first order novelties can be very hard. So it's almost like Maxwell's demon in a way, right? Except the demon is trying to trick you to react to novelties in a certain way that ultimately will be your downfall. And so how do you do those second order kind of thinking or reasoning? Is, I think it shows that reasoning is actually very important, because unless we do the first order reasoning, we would probably not be able to get to the second order reasoning if we only follow statistical principles. But you're right that in theory, yes, that can absolutely happen. And even in wargaming, etc., that would happen. So that is something that a good OWL agent would have to keep in mind, that agent novelties could be of that nature. And you also have that ability, right? So if the game is to win the war, then it could be that based on the model you have of your adversary, you also try to control. Your strategy might be to inject novelties as well. But then if you find that this is like a theory of mind, right? So if you feel like the other adversary has some sense of what you're doing and that you're going to inject novelties, then maybe you should not. So it's kind of, what do I think I know? And this can go on ad infinitum. So right. And that's kind of the strategic arms race, right? I think that when we're able to do that, because in a way it's kind of like game theory, but it's like a very high dimensional game theory if you think about it, right? Um, I mean, in normal game theory, as the furthest I go really is that that I'm trying to guess what you think I know, and then trying to base my decision on that, right? But then when you go like several orders, above that, it can quickly unravel and lead to paradoxes, right? And I think those are interesting problems. And it's quite possible that if we do end up building such agents, and that kind of problem will emerge sooner rather than later. I think we're still very far from that, but they have infinite memory basically to work with. So I would not put it past them to get to that stage. Right. Yes. And I think that's happening right now. I mean, the stock market is just going up, up, up. Yeah, no one can understand. They're like, what are these people doing? Like, but it does seem like there's a psychology behind it. And then maybe there's convergence at some point. I don't know, but it's a very interesting phenomena. I wonder if it's been studied. I can sort of maybe see very interesting game theoretic studies on that. But yeah, I think it's very interesting, by the way, to combine open world learning with game theory. We tried to do that. I showed one experiment with the iterative prisoner's dilemma. And we have also tried to apply it to poker. We've implemented a version of GNOME for poker that we are now trying, where we inject novelties and try to see what agents do or don't do. But I think that in if a a sort of theoretical framework for understanding agent novelties in particular is game theory. So if I'm in an interacting system of agents and I'm making decisions, and I know the payoff matrix and everyone else knows the payoff matrix, but maybe the payoff matrix changes for me. And so I start behaving differently. And do the other agents realize that, okay, something has changed and this has changed? And so, I mean, there are interesting problems that can be defined there. Yes. And that's what we are trying to do with this paper, right? We are saying that if you have two agents and one is optimal in some way, like one is getting 90%, the other one is getting 88%, but for the 88% agent, the best we can do when we try to look for a novelty that will break the agent, like the most impact we're having is like -5%. But for the 90% one, we can find a novelty that reduces performance by -50%. I think that kind of nuanced evaluation is not happening right now. Like we would just stop at the 88 and 90. We would say this one is 88, this one is 90, hence use the 90. But we are saying that if you use a framework like this, right, then you can provide more context that, okay, this is 88%, but it's more robust. And it's robust for this reason, because it's harder to find a novelty, or the best we can do to trip up this system is this minus percentage. Whereas for this other one, we can actually very easily find novelties that will, reduce it by 20, 30, 50%. So I think that the adversarial search one, et cetera, can sort of fit into that kind of thing as well. But to also answer the first question, right, which is that the implementation of the AI, I mean, the truth is that, in these applications, right, all three of these are already in many are being implemented or have been implemented. So it's not even hypothetical. The traditional AI has been implemented in all of these domains. We do have, biopsy scanning systems, and cybersecurity has a huge, AI component these days, the malware and so on. And there's an arms race in the cybersecurity going on. And even in the autonomous vehicles, right, we can sort of see that no matter how much they train it, it still only works well on highways. And even there are problems, right? So I think all three of these already, the traditional AI is already implemented, and there are more domains like that. And if we really want that AI to go to the next level and be trusted by humans, then we need OWL capabilities of some kind, because we can't teach it everything. So we need some kind of, robustness and ability to learn when something new occurs, because these are all continuous learning systems. They could be taken offline and a new version could be uploaded. But when you think about it, by and large, these are all continuous learning systems. They are continuously seeing data. Decisions are being made based on what they are seeing. And if they have OWL, then they can, I think, really help us to take the application to the next level, but they don't have it right now. And so that's impeding their application in a way that, we can only apply them in very limited settings, precisely because they are so brittle, and we can't ever trust them completely.